Hello, and welcome to Sleep Gravity. In a Hubble image, NGC 6723 appears like a very old chandelier suspended in the darkness of the Milky Way. Thousands of points of light crowd close together. Some shine more brightly, some more softly, and some sit so near one another that, at a glance, it is easy to forget that each tiny speck is a separate star. The image first gives us a feeling of deep stillness. There is no obvious motion, no horizon, no familiar object that helps us compare its size. There is only light, darkness, and an ancient cluster of stars holding its shape through gravity. The name chandelier cluster makes this star cluster feel a little more familiar. In everyday life, a chandelier may bring to mind old rooms, lights that have been lit many times, and objects that remain in one place through countless evenings. But the chandelier of the universe is not made of glass or metal. It is a globular cluster, an enormous community of stars located about 27,000 light-years from Earth, in the direction of the constellation Sagittarius. None of the lights inside it is reflecting a candle. Each one shines from a star, from matter so hot that the atoms within it exist under conditions very far removed from anything on Earth. The beauty of a globular cluster can easily make us stop at the feeling of sparkle. But to astronomers, a cluster like NGC 6723 is not only a beautiful scene, it is more like an archive of time. The stars inside it are not scattered at random like glowing dust thrown into the dark. They belong to a very old population, formed very early in the history of the galaxy, and most of them have traveled together through such a long span of time that the age of human civilization is only a very thin layer near the end of the story. A young star cluster is often still connected to gas, dust, cold clouds, and ongoing star formation. In such places, finding blue, hot, bright, massive stars is not especially surprising, because they may be newly formed stars, living through the most brilliant part of their lives. An ancient globular cluster is different. It is like a community whose strongest period of birth ended long ago. Most of the material needed to create many new stars is no longer present in the rich way it is inside young nebulae, and the stars within the cluster have had a great deal of time to reveal the consequences of age. The age of a star does not appear the way the age of a living creature does. It has no skin to wrinkle, no hair to turn gray, no slower walk for others to notice. A star carries its age in its light. Its color tells us about the temperature of its surface. Its brightness suggests the energy it is giving off. Its original mass deeply affects the speed at which it consumes fuel in its core. When many stars in the same cluster are placed on a map of color and brightness, they do not form a meaningless scatter of points. Instead, they arrange themselves into lines and branches that can be read like traces of stellar evolution. In that way of reading, the color blue has a special meaning. Blue stars are usually hotter and more massive. Because they are more massive, they force their cores to work harder, burn through fuel more quickly, and live shorter lives than smaller, cooler, redder stars. They are like large flames that burn brightly for a brief time, while lighter stars can quietly exist across much longer spans. After billions of years, in a very old star cluster, the massive blue stars from the original generation should have left the stable stage of stellar life long ago. So when a few bright blue points appear among an elderly population of stars, they do more than make the image more beautiful. They introduce a small irregularity into the order of the picture. If the entire cluster is like a slow piece of music written in the yellow and red light of age, then those blue points are like a few unexpected high notes sounding where the listener did not expect them. They are not numerous enough to change the whole melody, but they are clear enough for the ear to notice that something unusual is happening in the tune. Those stars are called Blue Stragglers. The name carries the feeling that they are straying out of line or lingering on a path that stars of the same age left behind long ago. They are bluer, brighter, hotter, and seem younger than most of the stars around them. On a map of color and brightness, they appear in the place where a younger or more massive star would usually be found. But their environment is an ancient star cluster where most members share the same very long history. The strange thing is not that the universe contains blue stars. Blue stars exist in many places. The strange thing is where they appear. A blue star in a young star-forming region makes sense. A blue star in an old cluster is more like a person with a very youthful face standing inside a family photograph taken many generations ago. That youthful appearance does not automatically prove that the person entered the frame at the very end, but it is enough to make the viewer look more closely at the history of the entire picture. The easiest explanation sounds very tempting. Perhaps blue stragglers were born later than the other stars. But in ancient globular clusters, that explanation is not simple enough to slide past all the evidence. These clusters are usually no longer environments rich in gas and dust, where new stars can form vigorously, as they do in young regions of the galaxy. If a star that looks young appears there, the origin of its youth may not lie in a simple late birth, but in a more complicated history, one in which matter, orbits, and gravity have interfered with the course of a star's life. A star does not necessarily live entirely alone. Many stars in the universe belong to binary systems, where two stars orbit one another for a very long time. If they are close enough, matter can move from one star to the other, changing the mass, temperature, and appearance of one of them. In crowded stellar environments, close encounters, gravitational interactions, and possible mergers can also leave deep consequences behind. A star that is already old may receive additional material, become hotter and bluer, and appear as though it has moved backward on the clock of evolution. But to fully understand how strange that is, we need to place blue stragglers back against the ancient background of the cluster. If a blue star is separated from its environment, it is only a hot point of light. If it is placed among thousands of old stars that have traveled together for more than 10 billion years, it becomes a sign. That sign is not loud. It does not disturb the stillness of the image. It only lets the viewer realize that the age of a star is not always a single straight line from birth to fading. Hubble helps make that sign clearer because it can separate stars in very dense regions, measure their colors and brightness, and place them together within the same evolutionary picture. A globular cluster then stops being a blurry patch of light and becomes a map of many stellar lives. Most of the points of light follow the predictable order of age and mass. A small number of blue points sit outside that order, far enough away to be noticed, rare enough to preserve the mystery, and real enough to force science to search for a more careful path of explanation. NGC 6723, then, is not only a beautiful chandelier in space, it is a gentle doorway into a deeper problem in stellar astronomy. How light can make a star look young inside a community that has already grown old. The blue color of blue stragglers is not a miracle that defeats time. It is a clue showing that time in the life of a star can be influenced by the relationships around it. A companion star, a stream of matter flowing across an orbit, a close passage through the core of the cluster, or a very rare merger, can change the shape of age as it appears in light. Within that ancient chandelier, blue stragglers are like lights that refuse to look their proper age. They do not deny that the cluster is old, and they do not turn it into a young star-forming region. On the contrary, it is precisely because the surrounding stars are so ancient that their youthful appearance becomes so noticeable. They give Hubble's quiet image an added layer of very gentle tension, not tension in the sense of danger, but the tension of a detail that does not quite fit, a small blue point that makes the entire story of stellar age feel deeper. To recognize that offbeat note, we first need to understand how a star reveals its age through light. What does blue tell us about temperature? What does brightness tell us about energy? How does mass determine the speed at which fuel burns? And why, inside an old star cluster, can one small blue point matter far more than its quiet appearance suggests? A small blue point inside an old star cluster only becomes strange when we understand what that blue color is saying. If we look only with our senses, the color of a star may seem like an aesthetic detail in an image of space, the way we might see a blue point, a yellow point, and a red point resting together against the dark, and call it the beauty of the sky. But in astronomy, color is not only there to make an image easier to look at. It is a physical trace. It tells us how hot the surface of a star is, how its light is distributed, and in many cases, it suggests which stage of life that star may be passing through. The human eye is used to color in a very familiar way. A hot object in everyday life may begin to glow red. A flame may contain regions of yellow, orange, and blue. A piece of metal, when heated strongly enough, can change color with temperature. Stars shine according to a broader principle of hot matter. A star does not emit light in only one single color, but radiates many different wavelengths at the same time. However, depending on its surface temperature, the strongest part of its light will lean more toward the red, yellow, white, or blue region. Cooler stars often appear redder. Hotter stars can appear bluish-white or pale blue. So when a star inside an ancient cluster is bluer than most of the stars around it, that blue is not just a beautiful shade. It tells us that the star's surface is hotter. A high temperature by itself is already important information, but it is not enough to tell the whole story. A blue star is often not only hotter, it is also usually more massive than many long-lived red or yellow stars. Mass is one of the deepest factors that determines the life of a star. It does not only tell us how much material the star contains, it also determines the pressure and temperature in the core, where nuclear fusion is turning hydrogen into helium and releasing energy. The more massive a star is, the more strongly its own gravity compresses its core. The more the core is compressed, the higher the temperature and pressure become, and the faster nuclear fusion can proceed. As a result, massive stars are often much brighter, much hotter, and yet they consume their fuel far more quickly. At first, this can seem counterintuitive. If a more massive star has more fuel, we might imagine that it should live longer, like a lamp with a larger oil reservoir burning for a longer time. But in stars, a larger reservoir usually comes with a far more powerful flame. A massive star does not merely have more fuel, it burns that fuel at a much more intense rate. It is like a brightly lit city using energy so quickly that even large reserves are not enough to extend its lifetime in a simple way. A smaller star has less fuel, but it burns more slowly, more economically, and therefore can endure across much longer spans of time. This is one of the most important ideas for understanding why blue stragglers are so puzzling. In an ancient globular cluster, the massive hot blue stars from the original generation should no longer remain in their youthful positions. They may have swollen into red giants, moved into more complicated late stages, or already ended the longest stable part of stellar life. Meanwhile, lighter stars are still slow enough to continue existing on the main sequence. If we look at the entire population of stars as a group that formed at nearly the same time, then after billions of years, the positions of the remaining stars on a map of color and brightness give us a kind of clock. That map is often called the Hertzsprung-Russell diagram, or, in many observations of star clusters, a color magnitude diagram. The name may not immediately bring an image to mind, but the idea beneath it is beautiful. Each star is placed on a plane according to its color and brightness. Hotter, bluer stars lie toward one side. Cooler, redder stars lie toward the other. Brighter stars occupy a different region from fainter ones. When thousands of stars in the same cluster are placed on the diagram, they do not spread out evenly like sand. They gather into a long line called the main sequence, then branch away as some stars leave the stable stage and begin evolving into giants. The main sequence can be imagined as the long road that many stars travel through for most of their lives. There, a star is balanced between two opposing tendencies. Gravity pulls matter inward, while the energy produced by nuclear fusion in the core creates pressure that pushes outward. When these two tendencies are in balance, the star can maintain a relatively stable state for a long time. Our Sun is also in this stage right now. It is not still in an absolute sense, but on the time scale of stellar life, it is going through a relatively stable portion of its existence, where hydrogen in its core continues to be converted into helium. For an old star cluster, the important point is not only that it has a main sequence, but that this main sequence is cut off at a particular place. More massive stars have left the main sequence first because they use up their fuel more quickly. Lighter stars remain behind. The place where stars begin to leave the main sequence is called the main sequence turnoff. It is like the age mark of the entire cluster. If the turnoff lies in a region of stars that are still relatively hot and bright, the cluster may be younger. If the turnoff has moved down into the region of lighter, cooler stars, the cluster is older. Astronomers can use this feature to estimate the age of a star cluster, not by asking each individual star, but by reading the overall shape of the entire population. Here, the beauty of science lies in patience. A star cluster does not state its age with a number already written out. It offers thousands of points of light, each one carrying a different color and brightness. Humans measure those lights, place them on the same diagram, and then recognize a curve, a turn-off point, an order. From that order, the age of the cluster gradually appears. It is like looking at a forest in late autumn. There is no need to ask each leaf how long it has lived. By looking at the colors, the thinning branches, the limbs already bare, and the canopies that remain green, we can sense how far the season has advanced. With stars, that feeling is replaced by data, but the idea still carries a similar gentleness. Age is read from small signs accumulated across an entire population. Blue stragglers create a place where that picture does not quite fit. They lie above and bluer than the cluster's turn-off point, in a region where, if we follow ordinary stellar evolution alone, the stars of the cluster should no longer remain. They are like people appearing outside the age line that the rest of the community has drawn. If a globular cluster tells us that massive blue stars left the stage long ago, blue stragglers appear like a few figures still standing under the lights. Not because time forgot to touch them, but because their histories may have been different. That difference is very small when seen only in a wide image. A few blue points among thousands of lights can easily be dismissed as minor details. But on the diagram, they stand out more clearly. A color magnitude map is like a way of removing some of the distracting sparkle of the image and preserving the real structure underneath. The ordinary stars in the cluster follow predictable regions. The stars that have aged follow their branches. The smaller stars continue burning slowly on the main sequence. And then there are the blue stragglers, sitting in a place that makes us ask why they still have such temperature and brightness. This also helps correct a small misunderstanding. When we hear that a star looks young, we should not imagine that it appears young in the way a human face might look young. In astronomy, young here is a way of speaking based on evolutionary position. A star that looks younger means its color and brightness resemble those of a more massive star, or a less evolved star, compared with the overall age of the cluster. It does not necessarily mean the star was recently born. It does not necessarily mean its true age is smaller than that of all the stars around it. It only shows that its present light does not match the simple path that a star formed at the same time should have followed. That mismatch is where the story begins to gain depth. If someone sees blue stragglers only as beautiful blue stars, they will miss the most important part. They are not special because blue itself is special. They are special because that blue appears in the wrong context. A new candle in a new room is not surprising. A candle that looks freshly lit inside an ancient temple sealed for thousands of years is what makes someone stop. With blue stragglers, the context is the old globular cluster, and the blue color is the first sign that something has interfered with the star's apparent age. There is another way to feel this. Imagine the entire star cluster as a very large classroom, where all the students entered at almost the same time. After a very long while, Most of them have moved through different levels according to their own pace. The strongest and fastest have left the classroom early. The slower ones are still there. If a few people suddenly appear to be at a much earlier stage than the history of the class would suggest, an observer would not only ask what they look like, they would ask what happened to them. Did they arrive late? Did they receive something from someone else? Or was the history of the class itself more complicated than the original record? For globular clusters, the explanation of arriving late is not as easy to accept as it is in an everyday example. An ancient star cluster is no longer a classroom that keeps receiving large numbers of new students. So the appearance of a few stars that look young forces astronomers to look toward other possibilities. Perhaps the star was once part of a binary system. Perhaps it received matter from a companion star, increasing its own mass and temperature. Perhaps two stars came close enough to merge into a new, more massive star. These possibilities do not turn blue stragglers into miracles. They bring them back to physics. Mass changes, fuel changes, the structure inside the core changes, and the light on the outside changes as well. But before those mechanisms can become convincing, the foundation of stellar age must be clear. Blue indicates high temperature. Temperature and brightness are often connected to mass and evolutionary state. Greater mass makes a star burn more strongly but live for a shorter time. An old star cluster has a turn-off point on the main sequence, showing that the original massive stars have already left their stable stage. Blue stragglers sit above that turn-off point, as though they have gained extra mass or an extra history that ordinary stars in the same cluster do not have. All these pieces connect to form the reason why one small blue point can matter. Without that foundation, blue stragglers can easily be told as something strange but thin. There are blue stars in an old cluster. It sounds unusual, and then the thought ends there. But once we understand how age is read from stellar diagrams, they become a real challenge to the way we imagine the life of a star. They show that a star is not only a sphere of hot gas, living entirely in isolation, according to its initial mass. In a universe with binary systems, crowded clusters, and gravity pulling objects into long-lasting relationships, the life of a star can be rewritten through contact with other stars. It is also important to remain precise here. Blue stragglers do not collapse the entire theory of stellar evolution. On the contrary, it is because stellar evolution theory works so well for most stars in the cluster that their deviation becomes easy to notice. If everything were chaotic, an exception would no longer carry meaning. But when most of the stellar population arranges itself into a clear order, the points that fall outside that order become clues. They do not deny the map, they mark the places where the map needs an additional layer of history. That makes blue stragglers suited to a very slow kind of curiosity. They do not astonish us with size. They do not frighten the listener with a violent ending. And they do not need to be exaggerated into immortal stars. They simply ask us to read light more carefully. They ask us to distinguish between true age, apparent age, and evolutionary path. They ask us to remember that in the universe, the present appearance of an object can carry traces of many earlier events, just as a quiet lake can still hold ripples from a motion that happened before we had time to see it. Within NGC 6723 and other globular clusters, blue stragglers therefore appear like small blue dots placed in the wrong position on the stellar clock. They are not loud, but they are persistent. They are not numerous, but there are enough of them to become a real scientific problem. They do not say that time has stopped. They say that time can become more complicated when stars do not live in isolation. An old star cluster does not only contain individual stellar lives aging beside one another, it also contains shared orbits, long-term interactions, exchanges of matter, and close encounters that can change the light of some of its members. From here, the simplest explanation begins to waver. If a blue star in an old cluster cannot easily be explained by late birth, then its youthful appearance must come from something else. Not from escaping time, but from changing the things that time depends on in order to show itself outwardly. Mass, fuel, core structure, and relationships with neighboring stars. A blue straggler, then, is not a star that has escaped old age. It is a star that makes old age harder to read. Its blue light is still real light. Its temperature is still a real temperature. Its brightness is still measured with real data. Only our first explanation needs to be expanded. A blue point inside the ancient chandelier is not an error in the image. It is a sign that the image contains more history than its quiet appearance suggests. When an old star cluster still preserves a few lights that look young, what we need to search for is not a miracle, but the physical path that brought those stars to their unusual positions on the map of stellar age. On a color magnitude diagram of an old star cluster, most of the points of light behave in a fairly orderly way. They do not fall randomly like dust on a sheet of paper, but gather into lines that can be read. Stars still in their stable stage lie on the main sequence. Stars that have moved farther along in their lifetimes turn off into other branches. The cluster's turn-off point shows where the more massive stars have gradually left the long stage of hydrogen burning. Once the eye becomes familiar with it, that diagram begins to resemble a clock, not with moving hands, but with an age mark written in light. And then, above that mark, slightly outside the place where they should be allowed to stand, there are a few blue points. There do not need to be many, just a few are enough to change the picture. An old star cluster may contain hundreds of thousands of stars, but sometimes the few members that refuse to sit in the right place tell the most fascinating part of the story. They do not destroy the entire map of stellar evolution. They do not make the familiar rules meaningless. On the contrary, they stand out only because the rest of the map is so orderly. When most stars follow paths that are predicted quite well, a blue point in the wrong region becomes a sign that its history contains an extra layer that a simple reading has not yet reached. These offbeat blue stars have drawn the attention of astronomers for many decades. They are recognized not because they are always the brightest objects in an image, but because their position on the stellar map does not match the age of the cluster. A blue, hot, bright star usually suggests greater mass, and greater mass usually means a shorter stellar life. In an old population, stars like that should have left the main stage long ago. Their appearance is like a new signature on an ancient document, not necessarily false, but certainly something that needs to be examined carefully. One interesting part of the phenomenon is how quiet it is. If the sky told stories in thunder, people would notice easily. A stellar explosion, colliding galaxies, a black hole tearing matter from a nearby star, scenes like these already contain their own drama. Here, the strangeness lies in a few points of light placed in the wrong position. There is no violent spectacle right in front of us, no enormous ring of fire, only a star that looks a little too blue, a little too bright, a little too young for the place where it lives. Science sometimes begins from small deviations like this, from a detail that does not shout, but remains there long enough to make the observer return to it. In an image of a globular cluster, the human eye is easily drawn into the dense beauty of the entire glowing mass. The stars crowd so closely together that the core can look like a glittering mist. But Hubble has an advantage that the eye and many ground-based telescopes do not, resolution high enough to separate many points of light that lie close together, especially in crowded regions. When each star is separated from the shared glow, its color and brightness can be measured individually. From there, the members that do not match their age begin to appear more clearly, no longer lost in the collective brilliance of the cluster. The cluster 47 Tucanae is a famous example in the history of studying these lights that fall out of line. In its dense center, Hubble once helped resolve stars that were difficult to separate clearly from the ground. In that crowded core, astronomers found blue stars that had been rejuvenated, shining with an appearance more like that of younger stars. The very concentration of these stars in a place where stars are extremely close together suggested that a star's environment can play a major role. A star in the core of a cluster does not drift through its life in absolute isolation. It lives among gravitational pulls, orbits, very close passages, and, in many cases, a long-term bond with another star. From far away, a globular cluster can seem motionless, but inside it, the stars are not still like bulbs fixed to a metal frame. They move continuously around a common gravitational center, changing position over long periods of time, pulled by the gravitational field of the cluster and by passing stars. The distances between the stars are still enormous compared with the sizes of the stars themselves, but in the core of a globular cluster, the stellar density is far higher than it is in the region around the Sunday. Across billions of years, even rare possibilities have time to become important. A blue straggler, then, is not merely a star with an unusual color. It may be a trace of the environment. It says that where a star lives can matter as much as the mass it was born with. If a star is born alone, far from other stars, its path may remain closer to a simple model of evolution. If it belongs to a binary system, the story becomes different. If it lies inside a crowded star cluster, where orbits can be disturbed over long spans of time, the chances for exchange, gentle collisions, or rare mergers begin to appear like branching paths in the life of a star. This point makes these falsely young stars especially interesting. They do not only help us ask about the age of a star, they reveal the social life of stars in a very physical sense. Stars have no intention, no choice, no memory, like human beings. But they do have gravitational relationships. They can orbit one another. They can pull matter across an invisible boundary. They can pass close enough for their orbits to change. Some can even merge into a new, more massive object. None of this requires consciousness in order to happen. It only requires gravity, time, and distances close enough. At this point, it is very easy to call these stars forever young, but that phrase is only accurate if we keep it as a soft image. They are not truly forever young. They still obey stellar physics. They still consume fuel, still evolve, and will still leave their current state when their internal conditions change. Their youth is a youth red from light, from their present color and brightness, not proof that they have escaped time. They are like a clock that has been reset after some event, but even if the hands have moved back to a different position, the mechanism inside continues to run. The word appear is very important here. A star that appears young is not the same as a star that has just been born. It may have existed for almost as long as the stars around it. The part that made it different may have come later, when it received additional material, increased its mass, became hotter, and shone more brightly. Its present light no longer tells a simple story from birth to now. It tells a story with interruptions, with interference, with an event strong enough to make the star appear in a younger region of the stellar map. Using a gentler image, we can imagine a globular cluster as a very old library, where most of the books have yellowed with time. The unusual blue stars are like a few books with newer, brighter covers placed on the same ancient shelf. They do not prove that the whole library was built recently. They also do not prove that those books have never passed through time. They only say that their history of preservation, repair, replacement, or joining is different from the rest. For stars, that cover is not paper, but light. The repair is not done by any hand, but by matter and gravity. This way of seeing helps us avoid a common storytelling trap. If we only say that this type of star is mysterious and then immediately give the explanation, the video becomes fast but thin. What needs to be preserved is the slowness of recognition. First, we see an old star cluster. Then we realize that the age of the cluster is read from a diagram. Then we notice a few blue points that sit too high, too bright, too hot compared with the shared age mark. Each layer makes the phenomenon fascinating on its own, without any need for exaggeration. It is like listening to a very even melody, then suddenly noticing that one small note does not fit. That note carries weight only because the ear has had time to become familiar with the regular rhythm before it. From a scientific point of view, the existence of blue stragglers also reminds us that a star cluster is not a collection of completely independent objects. It is a dynamical system. Its members are constantly moving within a shared gravitational field. Over time, more massive stars tend to sink toward the central region through a process related to the exchange of energy between stars. Binary systems can be tightened, disrupted, or pushed onto different orbits after close encounters. The longer a star cluster lives, the more time the traces of such interactions have to accumulate. This opens another role for those blue points that seem to have the wrong age. They are not only objects that need to be explained, they can also become tools for reading the dynamical history of the cluster. If many of them are concentrated in the core, that suggests a crowded environment, where close passages and strong interactions may happen more often. If they appear in less dense regions, long-lived, stable binary systems may play a larger role. Their distribution within the cluster, not only each individual star itself, becomes a clue to what has taken place across billions of years. This is where the story becomes wider, without leaving the subject behind. A blue star standing in the wrong position does not only tell its own story, it can tell the story of the place where it lives. It can reveal how crowded the cluster's core has been, whether binary systems have survived for a long time, and how strongly gravitational encounters have stirred the stellar population. A small detail on the color magnitude diagram suddenly connects to the larger structure of the entire cluster. From one blue point, we move toward the shared history of thousands, even millions, of stars. Even so, we should not turn every member that falls out of line into the same story. They are not all created by a single mechanism. Some may be strongly connected to mass transfer in binary systems. Others may be the products of mergers. In dense core regions, close encounters may be more important. In quieter outer regions, binary systems may survive long enough to evolve in a different way. This unusual group of blue stars is therefore not one simple answer, but a family of phenomena with multiple formation paths. That diversity is exactly what makes them a good subject for a slow journey, because each layer of explanation opens into another layer of environment. One thing remains constant across these possibilities. They seem to have gained extra mass compared with ordinary stars near the cluster's turn-off point. Mass is the key that changes the light. When a star receives additional material, or when it is formed from the merger of two lighter stars, it can become more massive than stars of the same age that remain on the main sequence. Greater mass compresses the core more strongly. Nuclear fusion can operate at a different rhythm. The surface becomes hotter, and the light becomes bluer. The stellar clock has not been erased, but the face of the clock has been changed. Looking back at the ancient chandelier of NGC 6723, the blue points with the wrong apparent age are no longer decorative details. They are like small notes inserted into an old piece of music, showing that the composition has been altered in a few places. The cluster is still old. Its ancient character has not disappeared. Most of its members still follow the shared history written very early on, but it is precisely against that old background that these falsely young stars have room to appear. They need an ancient stage for their offbeat presence to mean something. From here, the explanation that perhaps they were born later begins to feel too simple. An ancient globular cluster cannot easily provide the raw material for a significant young generation of stars. Observational signs have also led researchers to pay close attention to other paths, especially binary systems and close encounters in crowded environments. The blue appearance of these stars does not necessarily come from a younger true age. It may come from a change in mass, an episode of receiving additional material, or a merger that makes the new star look as though it has moved backward toward the younger side of the diagram. A Hubble image may hold everything in silence, but beneath that silence there is a great deal of long-term motion. Stars orbit the cluster's center. Binary systems revolve around one another. Matter can flow from one star to another. Orbits can be pulled off course through close passages. None of this unfolds at the fast rhythm of a human life, but on the timescale of a star cluster. Small changes can accumulate into a result bright enough to be seen. The offbeat blue lights among an old stellar population, therefore, do not only raise a mystery about age, they soften the idea that the life of a star is only a private, closed path from birth to the exhaustion of fuel. A star can carry the history of another star in its light. It can shine more brightly because it has received material that was not originally its own. It can look younger because two stellar lives once merged into one. It can stand in the wrong position on the cluster's clock, not because the clock is wrong, but because its story has passed through a different turning. At the end of this layer of understanding, what remains is not a complete answer, but a change in the way we look. A blue point is no longer just the color blue. It is temperature, mass, evolutionary position, environment, orbit, and perhaps the trace of a long connection with another star. When we look at an old globular cluster, we do not only see stars that have aged together. We see a place where age can be rewritten in a few members, very quietly, through gravity and matter. The easiest explanation is no longer wide enough. If these stars are not simply a late-born generation inside an ancient cluster, then we need to look for paths that can make an old star appear newer without creating it from the beginning. The first path begins with two stars orbiting one another for a long time, close enough that the boundary between one star's life and the other's is no longer entirely separate. Their age can be changed not by a miracle, but by a very real stream of matter flowing slowly through the space between two stars. A star, when seen from very far away, often gives us the feeling that it is living a completely separate life. It is only a small point of light within the cluster, producing its own glow, holding on to its own heat, consuming fuel in its core across very long spans of time. If we read stellar life in the simplest way, everything seems to begin with the star's initial mass, whether it was born heavy or light, how hot its core became, how quickly or slowly it burned its fuel, and then how it evolved along a path that mass had almost already drawn for it. This way of seeing is very useful because it explains much of the order inside an old star cluster, but it is not enough for the blue points that sit outside the shared line of age. Not every star lives alone. In the universe, many stars belong to binary systems or multiple star systems, where two or more unfamiliar suns are bound together by gravity and orbit a shared center of mass. They may be very far apart by the measures of human life, but that distance is not necessarily large enough to keep two stellar lives completely separate. The orbit of one star is tied to the other. A change in the mass of one member changes the balance of the entire system. And when one star grows older, expands, or loses matter, the other star can be pulled into a part of the story that it would never have experienced if it had lived alone. In a wide binary system, the two members can evolve almost independently. They are still bound by gravity, still orbiting one another through millions or billions of years. But the outer gas of one star is not close enough to be taken away by the other. One member may age first, the other may burn more slowly, and the relationship between them remains mostly orbital. In closer systems, that separation becomes thinner. When one star uses up most of the hydrogen in its core, its internal structure changes, the core contracts, the outer layers expand, and the star may enter the red giant stage. If it is alone, those outer layers simply swell into the surrounding space. If it has a companion close enough, the expanding gas can enter a region where the gravity of the other star begins to claim influence. In a two-star system, there is an invisible gravitational boundary around each member, often called the Roche lobe. We do not need to turn that boundary into a formula. We only need to understand that matter near one star is usually held by that star. But when the outer layers expand too far, some of the gas can cross the region of balance and be pulled toward the other star. When this happens, hot gas from the swollen star no longer belongs entirely to it. Matter begins to flow through the space between the two members, following the geometry of gravity and orbit, then falling toward the receiving star. It is not water flowing from a vessel, but hot plasma, guided by gravity, moving through an environment where everything is rotating, being pulled, and changing very slowly over time. This process can last so long that, in a still image, it leaves almost no feeling of motion. One star loses matter little by little. The other receives portions of gas. The shared orbit changes very slightly. After millions of years, the result can become much clearer than any of the small moments that created it. The member that loses matter may reveal an older, dimmer core and eventually become a white dwarf that is difficult to notice. The member that receives matter becomes more massive than it was at the beginning. The increase in mass changes the pressure and temperature inside it. The core is compressed more strongly. Nuclear fusion may proceed with a new rhythm. The surface becomes hotter, and the light leans more toward blue. On a color magnitude diagram, it may shift into the region where a younger or more massive star would usually appear. This path helps explain how a star in an old cluster can look young without needing to have been born late. It may have formed very early, at nearly the same time as most of the stars in the cluster, but later received additional matter from a companion. What changed was not its birth date, but its present mass, its internal structure, and the way it shines. Its blue light does not say that time has reversed. It says that the star's life once passed through a relationship close enough for matter from another star to become part of it. The almost paradoxical detail lies in the roles of the two members of the system. The star that was originally more massive usually ages first because it burns fuel more quickly. When it leaves the main sequence and expands, it can become the source of matter for its companion. The star that was originally lighter, which should have continued burning more slowly and quietly, receives additional material and becomes brighter, hotter, and bluer. In the end, the star that looks younger in the image may be carrying matter from a star that aged before it did. That apparent youth is not a resistance against time, but the consequence of two stellar histories touching each other within a shared gravitational system. From far away, this entire complicated process collapses into a single point of light. A blue point on the diagram does not announce that two stars once orbited one another, that one star expanded, that matter crossed a gravitational boundary, or that the orbit of the whole system was adjusted by the loss and gain of mass. It only shows the result, one member that is hotter, brighter, and standing in a region that an old cluster cannot easily explain through single-star evolution. Behind that position may be billions of mutual orbits, a long process of mass exchange, and a bond so lasting that the apparent age of one star has been rewritten by the matter of another. In globular clusters, time is always working quietly. A binary system can survive across spans so long that all familiar human measures become far too small. At first, the two stars may simply orbit one another without exchanging anything significant. Then one member evolves more quickly, its outer layers expand, the gravitational boundary is crossed, and matter begins moving toward the other star. The cluster does not need to form an entirely new generation of stars in order to create a few blue points with mismatched ages. It only needs to preserve binary systems that are close enough, long-lived enough, and stable enough for that slow process to be completed. The binary system explanation keeps the broader picture of the cluster intact. Most of the stars still age along paths that match their initial mass. The turn-off point of the main sequence still tells us the age of the population. The lighter stars still burn slowly. The original massive stars have still left their old positions long ago. Only some members, because they live under special orbital conditions, are pushed out of their ordinary positions. The stellar map is not wrong. It simply contains a few small symbols for lives that have been changed by close interaction. A blue light with a mismatched age may contain matter that once did not belong to it. The atoms now located in its outer layers may once have been inside another star, pulled out of an expanding envelope, carried across the shared gravitational region, and absorbed into the receiving star. After becoming part of the new structure, they do not carry separate labels of origin, but their consequences still appear in mass, temperature, and brightness. When that star shines, its light is no longer the pure story of a single object. It is more like the physical echo of two stellar lives that once came close enough to share matter. The concept of age, therefore, becomes less linear. A star can have a true age nearly equal to the age of the cluster, while its apparent age on the diagram looks younger. It may have been born very long ago, but later been fed with additional matter. It may stand in a bluer region, not because it has just formed from primordial gas and dust, but because its present mass is no longer the same as its birth mass. If the age of the cluster is a long sentence written with thousands of points of light, then the blue members that fall out of line are like a few words rewritten in different ink, not erasing the old text, but adding another layer of history to it. Mass exchange can also change the orbit. When one star loses mass and the other gains it, the gravitational balance within the system changes. The distance between the two members can shift, the speed at which they orbit one another can change, and if the material does not fall directly onto the surface of the receiving star, it can form an accretion disk, circling the star before gradually falling inward. The gas in the disk heats up, shines, and then joins the receiving star along a path that is far from simple. Even when these small details are not always clearly visible in each distant cluster, they show that mass exchange is a rearrangement of the entire binary system, not a simple act of adding and subtracting. Not every binary system creates a blue star with a mismatched age. Some pairs are too far apart to exchange matter. Some are disrupted before they reach the right stage. Some exchange matter but do not produce a member hot and bright enough to stand out on the diagram. Some stars receive matter and then continue evolving too quickly, leaving the region where they are easy to recognize. For a blue point to appear inside an old star cluster, many things must come together: orbital distance, initial mass, evolutionary stage, the rate of mass loss, and the ability of the binary system to survive for a long time in a crowded stellar environment. The environment of a globular cluster is not completely still either. In the dense core, stars are far more numerous than they are in the region around the Sunday. They are still very far apart by ordinary measures, but across billions of years, close passages can accumulate into real effects. A binary system can be pulled slightly off course by another star passing nearby, making its orbit tighter, wider, or more distorted. In stronger cases, one member can be replaced, the binary can be broken apart, or the orbit can be pushed into a state that later becomes more favorable for mass exchange. A globular cluster may look like a static object in an image, but inside, it is a long-lasting network of motion. Stars travel around the shared center. Binary systems revolve around one another. Close encounters change orbital energy. More massive stars can gradually concentrate toward the central region, while lighter members may be pushed farther outward. Over very long spans of time, the cluster is not only a stage on which stars shine, but also an environment that continually edits the way binary systems evolve. A blue star with a mismatched age can tell the story of the binary system that created it, while also telling the story of the place where that system existed. If a region in the cluster preserves many stable binaries, slow mass exchange may play a major role. If the core is too crowded, close encounters may alter orbits more strongly, or break apart fragile binaries before they have time to create a member with a mismatched age. The distribution of these blue points within the cluster becomes a clue to its dynamical history, not only to the evolution of individual stars. In some cases, the star that received matter still has a companion that leaves an observable sign. Its motion may wobble periodically, showing that another object is pulling on it in orbit. Its spectrum may shift slightly back and forth as it moves toward us and then away from our line of sight. The companion may have become a faint white dwarf, difficult to see directly but still leaving behind a gravitational influence. In other cases, the neighboring trace has faded because the binary system has changed too much, or because the two stars have reached a deeper ending, merging into a single object. When two stars approach the point where they can no longer maintain their separate distance, the story shifts from exchange to merger. A very close binary system can enter a common envelope phase, where the two stellar cores move together inside a surrounding layer of gas. Friction causes the orbit to shrink, orbital energy is transferred into the gas, and the system can follow several different paths. Sometimes the outer layers are expelled, leaving behind a tighter stellar system. Sometimes the two cores move inward and combine into a new, more massive star. The result may be a hotter, brighter member standing above the cluster's turn-off point, like a star remade from two older histories. A merger does not need to be imagined as a loud explosion. On astronomical timescales, it can be the final section of a long process, where the orbit gradually tightens, matter is pulled and mixed, the internal structure changes, and two objects become one. The star after the merger is no longer a copy of either original member. It has a new mass, a new structure, perhaps a different rotation rate, and its outer light may carry it into a bluer region of the diagram. It is not new in the sense of having just been born from a young cloud of gas and dust, but it is new in the sense that two stellar lives have been joined into a different physical state. Between mass exchange and merger, there are many shades. Some stars receive only enough matter to look younger. Some move deeply into a shared orbit and then merge. Some leave behind a faint companion, while others become single stars after the event. The group of blue stars with mismatched ages is not a phenomenon with only one formation path. They are more like a family of phenomena made of several related stories, all ending with a hotter, brighter appearance inside an old cluster, but reaching that point by different routes. The common factor remains mass. The more massive a star is, the hotter and brighter it usually becomes, and the faster it consumes its fuel. If a star in an old cluster has more mass than the remaining stars around the turn-off point, it will no longer sit in its old position on the map of age. Mass exchange can create that. Merger can create that. Close encounters in a crowded environment can support or trigger those paths. The blue light is the visible surface of a deeper change in the amount of matter the star is carrying. These members with mismatched ages do not weaken the theory of stellar evolution. They make it richer. A simple model of single stars explains most of the cluster's order, but a real star cluster does not contain only single stars. It contains binaries, multiple star systems, crowded cores, close encounters, altered orbits, and private histories that cannot be read only from initial mass. When those elements are added, the blue points in the wrong positions are no longer errors in the map. They become symbols marking the places where the map has met a side road. In the light of a falsely young star, there may be matter from another star. In its present brightness, there may be the trace of an orbit that once became closer, an episode of expansion, a stream of gas stretched through space, or a merger that erased the boundary between two objects. It is still a real star, with a real temperature, real mass, and real light. Only the story behind that light is no longer as straight as it first seemed. The old cluster, therefore, becomes a place where two kinds of time coexist. There is the shared time of the population, read through the main sequence turnoff, and the distribution of thousands of stars. There is also the private time of some stellar systems, where close orbits change mass, where a companion can transfer material, where two stars can blend into one. Shared time tells us that the cluster is ancient. Private time explains why, against that ancient background, a few blue points still look as though they arrived late. A blue point in the ancient chandelier is no longer an object standing outside age. It is a place where age has been mixed. It carries the traces of closeness, exchange, and movements so long-lasting that human beings can hardly sense them directly. It is not young in the way a new star has just been born in a young cloud of gas and dust. It is young in the way its present light has been remade by matter from another history. From the path of binary systems, the picture opens toward a stronger and rarer path in sparse stellar regions, very close encounters between stars in crowded environments. When the distance is not only close enough for matter to flow, but close enough for two stellar structures to deeply distort one another, a globular cluster can create a new member by joining two old stars together. There, the mismatched blue appearance no longer comes from slow sharing, but from a merger that rewrites mass and light into a single form. In the sparse regions of the galaxy, a star can pass through most of its life without ever coming close enough to another star to be deeply transformed. The distances between stars are usually so large compared with the sizes of the stars themselves that two unfamiliar suns can both belong to the Milky Way, both move within the same broad gravitational field, and still never touch each other in a physical sense. The region around the Sun is such a place. Neighboring stars are separated by gaps so wide that even light takes years to travel from one star to another. In an environment like this, direct collisions between stars are almost never a familiar part of stellar life. The core of a globular cluster carries a different rhythm. There, many stars are held inside a much smaller volume of space than in the sparse stellar regions of the galaxy. They are still not close together in the way objects in everyday life are close together, but the higher stellar density makes near passages more significant over long periods of time. A truly close encounter is still rare. A star does not constantly crash into another star like grains of dust in the wind. But if the cluster has existed for billions of years, events with small probabilities still have a great deal of time to happen. In an image, a globular cluster may appear motionless, like an ancient mass of light. That feeling comes from its immense distance and from the very short span of human observation. Inside the cluster, each star is still moving around the shared gravitational center. Their orbits are not perfect circles drawn in neat lines, but paths that keep changing very slightly as one star is pulled by another passing nearby. A star may travel deep into the core, then move outward again. A binary system may encounter a single star. Two binary systems may pass near each other. In encounters like these, gravity does not need to touch the surface of a star in order to change its life. It only needs to pull strongly enough, closely enough, and long enough during the moment when orbits cross. If two single stars pass each other at a very close distance, they can distort each other's outer layers through gravitational tides. Part of their orbital energy may be transferred into internal oscillations within the stars. Sometimes, instead of simply sweeping past each other and separating, the two stars may lose enough energy to become a bound system. In an even closer case, their outer layers may touch, mix, and eventually lead to a merger. Events like these are not common in an everyday sense, but in the core of an ancient globular cluster, where so many stars have been moving together for such a long time, they cannot be treated as having no role. This path is different from mass exchange in a closed binary system. In a binary, two stars may share material through a long process that begins when one member expands and its outer gas crosses a gravitational boundary. In close encounters or mergers, the change can come from two stellar structures being pushed into a deeper interaction, where their orbits and outer shapes can no longer remain as independent as before. In many cases, the final result still looks similar on the observational surface: a new star that is more massive, hotter, brighter, and positioned higher and bluer than the cluster's age turn-off point. A star after a merger is not a child, in the sense of being born from the primordial gas and dust of a young nebula. It is the product of matter that once belonged to two older stars. Two cores, two outer layers, two histories of nuclear fusion, and two earlier orbits are brought into a new state. After the process settles, the merged object may have more mass than either original member, and it is that new mass that makes it brighter, hotter, and bluer. On the color magnitude diagram of the cluster, it appears as a member with the wrong age, not because the cluster has just created a new young generation, but because two old life paths have joined into a different line of light. This helps explain why globular clusters are natural places to look for unusual blue members. They are old, crowded, and long-lived enough for rare interactions to accumulate. The old age of the cluster creates the ancient background that makes a blue star stand out. The high stellar density creates the possibility of close encounters, orbital exchanges, or mergers. The long stretch of time allows slow, rare, or condition-dependent processes to have the chance to reach completion. Without one of these three elements, the story becomes weaker. A young population with blue stars is not surprising. A sparse region has fewer opportunities for close encounters. A cluster that is not old enough has not yet produced the clear age mismatch seen in ancient clusters. In the core of a globular cluster, binary systems play an especially important role in close encounters. A single star passing near a binary system can exchange energy with the two members inside. If it comes close enough, one of the three stars may be thrown outward, while the passing star is captured as a new member of the system. Or the orbit of the two stars in the binary may become tighter, bringing them closer together over time. The tighter a binary becomes, the greater its binding energy, and later encounters can turn it into a powerful source of interaction within the cluster. Many paths to merger do not begin with two single stars rushing directly into each other, but with binary systems that are gradually edited by the shared environment of the star cluster over a very long time. When two binary systems encounter one another, the picture becomes even more complicated. Four stars pulling on one another through gravity inside a small region of space can produce outcomes that are difficult to predict by intuition alone. One member may be flung outward at a higher speed. Two stars may form a new binary system. One pair may be pushed close enough to exchange matter or merge later on. Across billions of years, a globular cluster does not only hold stars together inside a great sphere. It continually creates opportunities for orbits to be rearranged. The blue lights with mismatched ages may be traces of those rearrangements. A stellar merger does not necessarily leave behind a noisy image in the present. An event that happened very long ago may now appear only as a more stable blue point of light in an observation. Like a lake that has become calm after something fell into it, with only a few faint ripples remaining far away. A star cluster can hide the turbulence of its past beneath the still appearance of an ancient stellar population. Astronomers do not directly see every merger that has ever occurred. They see the result after it has cooled, settled, and blended into the wider picture of the cluster, while still standing in the wrong position on the map of age. A star after a merger may rotate faster than normal. The two original stars both carried orbital motion, and when they combine, some of that motion can become the rotation of the new object. A high rotation rate can affect the internal structure, the way matter is mixed, the slightly flattened shape of the star, and the way it shines. Not every unusual blue member rotates rapidly in the same way, but rotation is one of the traces astronomers can examine when trying to distinguish between different formation paths. If a star is both too blue for its cluster and unusual in its rotation or chemical composition, its story may include a deeper interaction event than that of an ordinary single star. Internal mixing is important. When two stars merge, material from different layers can become partly mixed. If hydrogen from outer regions is brought into a region where it can participate in nuclear fusion, the new object may extend its stable burning stage or appear younger on the diagram. This is not simply refilling an empty fuel tank. A star is a layered structure, with temperature, pressure, and composition changing with depth. A merger can disturb those layers, move material into new places, and then allow the star to settle into a structure unlike either of its original members. It is precisely this stability after the event that makes these stars easy to misread at first. A merged object, once it is settled down, may no longer carry the outward appearance of two stars that once collided. It is just one star, one point of light, one position on a diagram. It has no visible seam, no crack across its surface, no obvious signs saying that two histories once met. Astronomy has to read indirect signs: higher mass, bluer color, brightness that deviates from the turn-off point, position within the cluster, the possible presence or absence of a companion, rotation speed, spectrum, and the distribution of the entire group of similar members. Not every merger begins with a direct collision in one simple encounter. Some may be the final stage of a very close binary system. Two stars orbit one another, gradually lose orbital energy through interaction with matter or through other processes, and then enter a state where they can no longer preserve two separate outer layers. A common envelope may surround both cores. Within that envelope, the two cores move as if they are passing through a medium far denser than ordinary space. Friction causes the orbit to shrink. Orbital energy is transferred into the gas. If the envelope is expelled, the remaining system may be extremely tight. If not, the two cores may merge and leave behind a single, more massive star. Other cases may be driven by the crowded environment of the star cluster. A binary that was not originally close enough to merge may have its orbital distance reduced by a close encounter. A third star can make the binary's orbit more elongated, causing the two members to pass very close to each other during one part of their cycle. Through many such events, the system may gradually move towards stronger mass exchange or merger. A globular cluster does not need to create a direct stellar collision in order to produce an unusual blue point. It can work through many small influences, each one adjusting the system a little, until the binary enters a path it might never have followed if it had lived in a sparse region. This way of seeing makes a globular cluster feel like an environment with memory. Not conscious memory, but memory stored in orbits, in the distribution of stars, in binary systems that have survived or been disrupted, and in merged objects shining from positions that do not match their age. The older a cluster is, the more time its interactions have had to leave marks. Thousands of passages may create nothing significant. A few close enough encounters may change orbits. Some may bring two stars into mass exchange. More rarely, two stars merge, and afterward appear as a quiet blue light against an old stellar background. That rarity does not make the phenomenon less important. In the science of star clusters, a small number of objects can sometimes be the key to processes that are difficult to see. Most stars in the cluster tell the story of ordinary evolution. A smaller group tells the story of interaction. If we look only at the majority, we understand the shared age of the cluster. If we look at the exceptions, we understand how the cluster's inner environment has operated. These blue members with mismatched ages therefore become small markers on a dynamical map. They point to places where stars have not only aged, but also encountered, exchanged, been pulled, and been joined together. One point must remain very clear. A stellar merger does not make a star immortal. It does not allow the new object to escape stellar evolution. Greater mass can make it brighter and hotter, but it can also make it consume fuel more quickly than lighter stars. Its present youthfulness is not a promise of an infinitely long life. It is a new stage in a process that is still bound by physics. After being created or made more massive, that star will continue to evolve. It only appears, at the moment of observation, as a younger member compared with the shared age of the cluster. That makes the phrase, "stars that refuse to grow old," more beautiful if we understand it gently. They do not resist old age by breaking the rules. They only make old age harder to read. A star may have lived for a long time, but if it receives additional mass or forms from two older stars, its light no longer reflects a solitary life path. It carries within itself part of the history of interaction. It does not say that time has disappeared. It says that time can pass through multiple objects and then meet again in a new form. When Hubble looks into globular clusters, the important thing is not only that it captures the beauty of dense stellar regions. Its high resolution helps separate individual members in the cluster's core, where many stars appear very close together in the observed sky. Color and brightness data allow each star to be placed on a diagram. The positions of the unusual blue members show how far they deviate from the turn-off point. Their distribution in the core or in the outer regions helps suggest which mechanism may be more important. If a group is strongly concentrated in the crowded core, close encounters and mergers may deserve more attention. If they appear in places where binary systems can survive for long periods, slow mass exchange becomes a more compelling path. There is no absolute boundary that cleanly separates the two mechanisms. A binary system may be affected by the cluster environment and later exchange matter. A long process of gas transfer may eventually lead to merger. A close encounter may create a new binary system, and that system may later produce a blue member with a mismatched age. Many paths cross, separate, and meet again in the same observational result: a hotter, brighter star positioned where it appears younger than the rest of the cluster. It is this crossing of paths that keeps the subject from closing into an answer that is too neat. It is like a network of possibilities, but all of them turn around one central idea: mass and interaction history can rewrite light. In the core of a star cluster, a close encounter between stars does not necessarily have to leave two objects attached to each other immediately. Sometimes the result is only an altered orbit, a binary made tighter, a star thrown outward into the outer regions, or a pair of stars pushed into a state that will exchange matter later. The effect of an event may not appear immediately in the color of a star. It may wait millions or billions of years before becoming a blue point on the diagram. A cluster is like a system where cause and effect can be separated by spans of time so long that, without models and data, human beings would struggle to connect them. A star after merger may carry another sign as well. The chemical composition of its surface may differ from that of ordinary stars in the same region. If material from the interior has been mixed upward, or if the star received matter from the already altered outer layers of a companion, the elements at the surface may appear in slightly different proportions. That trace is not always easy to measure, especially in distant and crowded clusters, but spectroscopy allows astronomers to search for clues like these. Light, when separated into absorption and emission lines, does not only tell us how hot a star is, it also tells us which elements are present on its surface, and sometimes suggests what may have happened before. Each individual sign may not be enough to conclude a complete history. A rapidly rotating star has not necessarily merged. A blue member in the core has not necessarily been created by collision. A star with a companion has not necessarily received matter in a way that produced a youthful appearance. Science does not read these signs as solitary answers, but places them beside one another. Position on the diagram, distribution within the cluster, orbital motion, rotation speed, spectrum, the possible presence of a white dwarf companion, and the density of the surrounding environment all form a profile. From that profile, the origin of each group of blue stragglers is understood through probability, through models, and through the agreement between many pieces of data. This is why these members with mismatched ages still keep a gentle sense of mystery. Even when the main mechanisms are known, we have reasonable paths: mass exchange, merger within a binary system, collision or close interaction in the cluster core. We have data supporting the major role of binary systems. We have observations showing that the cluster environment affects their number and distribution. But each individual star can still carry a history that is difficult to reconstruct completely, because the event that created it happened long ago. Its companion may have faded, its orbit may have changed, and the present image is only the final result of many earlier steps. That incomplete certainty does not weaken the story. It keeps the story faithful to real science. Blue stragglers are not an exaggerated mystery, and they are not a puzzle solved so completely that all depth has disappeared. They sit in between, understood well enough that they do not need to be made mystical, but complex enough to keep teaching us how stars live in crowded environments. They show that when many stars are held together inside an ancient cluster, Stellar evolution and dynamics are no longer two separate stories. The core of a star and the orbit of a star, the fuel inside and the environment outside, the present light and the history of encounters, can all come together in one small blue point. Within the ancient chandelier of the galaxy, a merged star does not shine like a loud announcement. It simply sits there, slightly bluer, slightly brighter, slightly more out of step with its age than its neighbors. But if we follow its trace, we enter the deep interior of the cluster, where stars have moved around one another for billions of years, where binary systems have been pulled, tightened, broken apart, or joined again, and where some close encounters were strong enough for two stellar histories to end inside the same object. This way of looking makes the Hubble image feel less still. Beneath the quiet appearance of thousands of points of light is a long history of motion, contact, and remaking. A globular cluster does not need to be young in order to have a few lights that look young. It only needs to be old enough for rare interactions to have time to happen, crowded enough for close encounters to become meaningful, and stable enough to preserve their traces within the stellar population. An unusual blue member may be the product of matter transferred from one star to another. It may also be the result of two stars once coming too close, then blending into a new structure. In both cases, what we see is not primordial youth, but age that has taken a detour. After understanding these two paths, what remains is the way human beings recognize them among a dense crowd of stars. The blue points do not step out of the image and tell us where they came from. They must be separated from the cluster's shared light, measured through multiple filters, placed on a color magnitude map, compared with the main sequence turnoff, and then examined through motion, spectra, and position within the cluster. Their beauty is only the outermost layer. Beneath that layer is a very patient work of observation, where Hubble and other telescopes turn a glittering star cluster into a map of age, interaction, and stellar lives that once touched one another. When a globular cluster is seen with the naked eye or through a small telescope, it can look like a soft patch of light resting against the dark sky. Its outer regions may separate into a few scattered points of starlight, while the core often blends into a dense, smooth glow, almost like mist. Within that beauty, each individual star is hidden by the crowding of the whole population. A member that is bluer, brighter, and standing in the wrong place in the cluster's history of age can be swallowed by the shared background light, if the observing tool is not sharp enough to separate it from thousands of nearby lights. Hubble changes that view through one very important ability: resolving stars in crowded regions. Above Earth's atmosphere, the telescope does not have to look through layers of constantly shifting air, and its images of stars are not blurred in the same way ground-based telescopes often experience. When Hubble turns toward a globular cluster, many points of light that once blended together can be separated more clearly. A region that once looked like a faint glowing cloud begins to become a collection of individual stars, each with a measurable position, color, and brightness. Separating the stars from one another is only the first step. A beautiful image helps the human eye recognize the sparkle, but to know which star is deviating from the shared age, astronomers need to turn light into data. They measure how much light passes through different filters, compare brightness across different color bands, and use those measurements to infer the color, apparent temperature, and position of each star on a color magnitude diagram. The image is no longer only a picture. It becomes a vast record, in which each point of light is returned to its proper place on the map of stellar evolution. A filter in astronomy is like a selective doorway for light. It does not allow all wavelengths to pass through at once, but lets one particular range be recorded more clearly. When the same star cluster is observed through multiple filters, Hubble can show which stars emit more strongly in blue, red, or ultraviolet light. Hotter members often leave a stronger signal at shorter wavelengths. For blue stragglers, ultraviolet light is especially useful because hot stars stand out more in this region than many older, cooler, redder stars in the cluster. A point of light may not look especially striking in an ordinary visible light image, but when the ultraviolet window is opened, it becomes clearer as a member with a different temperature from most of its surroundings. Ultraviolet light is not a color the human eye can see directly. It lies outside our natural range of vision, but instruments on telescopes can record it, measure it, and turn the data into images or numbers. This is very important in globular clusters, where the core contains many stars that appear close together on the observed sky. A hot blue member can reveal its difference more clearly in ultraviolet light, helping astronomers recognize it within the crowded background of old stars. Hubble does not make the star bluer. It only opens a doorway of light that the human eye cannot open by itself. After the data is collected, astronomers do not simply look at the image and choose a few points that seem blue. They build a diagram. Each star is placed in a position according to its brightness and color. The crowd of old stars arranges itself into familiar branches. The main sequence stretches toward the turn-off point. The red giant branch reaches into the region where stars have left the stable stage. Small, faint, long-lived stars occupy another region. Once the general order has appeared, the falsely young members do not need to introduce themselves. They lie above and bluer than the turn-off point, in a region where single stars from the same generation should no longer appear in large numbers. This is a very different moment from discovering a new object suddenly brightening in the sky. These stars may have been in the data from the beginning. They did not appear all at once. They only become meaningful when placed beside the entire population. A blue point in an image may only be a blue point. A blue point located in the proper anomalous region of an old cluster's diagram becomes evidence that needs to be explained. The color magnitude map helps move curiosity from feeling to structure, from beauty to physics, from the question, "What does this star look like?" to the question, "Why is it there?" This work requires care, because globular clusters are extremely crowded. Two stars lying close together in the sky may be recorded as one shared point of light if the resolution is not good enough. A pair of faint stars, when blended together, can look brighter than a single star. A light source in front of or behind the cluster, not truly belonging to it, can also become mixed into the data. Interstellar dust can redden the light slightly. Measuring instruments have their limits. Each small factor can make a star look more or less displaced than it really is. Before calling a point of light an unusual blue member of the cluster, astronomers must filter out the possibilities that could cause confusion. The membership of a star in the cluster also needs to be checked. A point of light lying along the same line of sight does not necessarily belong to the globular cluster. It may be a foreground star in the Milky Way, much closer to Earth. It may also be an object far behind the cluster. Measurements of proper motion, radial velocity, color, brightness, and position help determine whether that star is truly moving with the cluster. If it does not belong to the cluster, its blue appearance no longer says much about the age of the cluster. If it is a true member, its age mismatch becomes a valuable clue. Proper motion is one of the subtle ways to do this. A globular cluster is not absolutely still against the sky. Its members share a common motion through space, even though each star also has its own motion within the cluster. When Hubble or other telescopes observe the same region over many years, the positions of the stars can be compared with great precision. Stars that belong to the cluster tend to move together across the sky, while foreground or background stars move differently. That very small shift helps separate true members from points of light that only happen to lie in the same direction. Once a blue member with a mismatched age has been identified, the next question does not stop at color. Astronomers want to know whether it still has a companion, whether it rotates quickly or slowly, whether its surface has an unusual chemical composition, whether it lies in the dense core or a quieter outer region, and whether it belongs to a group with a special distribution inside the cluster. Each kind of data opens another small window into the star's past. No single window shows the entire story perfectly, but when they are placed beside one another, the formation paths begin to appear more clearly. If a falsely young member belongs to a binary system, its light may reveal orbital motion. As it moves around a shared center of mass with its companion, it sometimes moves closer toward us and sometimes moves farther away. That change makes the spectral lines shift very slightly through the Doppler effect. By measuring the shift over time, astronomers can infer the presence of a companion object, even when the companion is too faint to see directly. If the companion is a white dwarf, that fits very well with the scenario in which one star aged first, lost its outer layers, left behind a faint core, while the other star received matter and became bluer. Spectroscopy also tells us more than overall color. When the light of a star is separated into wavelengths, dark and bright lines appear like fingerprints of the elements on its surface. Hydrogen, helium, carbon, oxygen, calcium, and many other elements leave their own signs. A star that once received matter from a companion may carry some chemical differences compared with ordinary stars in the same region, depending on which layer of material was transferred and what evolutionary stage the donor star had reached. A star after a merger may also show signs of internal mixing or a different rotation speed. These signs are not always easy to read, but they turn light from an outward appearance into a physical record. Rotation speed is another clue. If a star receives matter from an accretion disk, or if it is the result of two stars merging, it may rotate faster than a normal star of the same type. Rotation broadens the spectral lines, because one part of the surface is turning toward the observer, while another part is turning away. By measuring that broadening, astronomers can estimate the rotation speed. A high rotation speed does not tell the entire origin story by itself, but if it appears together with a displaced position on the diagram, signs of a binary system, or a location in the crowded core, it adds one more piece to the picture. Position within the cluster also matters. A member with a mismatched age located deep in the dense core suggests a more interactive environment. There, close encounters can alter orbits, tighten binary systems, or, in rare cases, lead to merger. A member located in the quieter outer regions may be more closely connected to long-lived binary systems that are less often disrupted by close passages. The overall distribution of the entire group within the cluster can reveal which mechanism is playing a larger role in each environment. It is not only each individual star that matters. The way the group as a whole is arranged inside the cluster is also a form of data. In some clusters, the unusual blue members may be concentrated in the core. In others, they may appear more often in the outer regions, or they may have a more complex distribution. This reminds us that there is no simple formula that applies to every globular cluster. Each cluster has its own density, its own age, its own dynamical history, its own number of binary systems, and its own past of interactions. The stars with the wrong apparent age are part of that environment. They are like small particles in a larger current, carried by the flow while also revealing how that flow has moved in the past. When many globular clusters are observed together, the picture becomes wider. A single cluster may tell a few local stories, but a survey across many clusters allows different environments to be compared. Do places with more binary systems also have more blue members with mismatched ages? Do places that are too dense break binary systems apart before they have time to exchange matter? How do the core and the outer regions differ? How are stellar density, the frequency of close encounters, and the survival of binary systems connected? Questions like these move the unusual blue stars beyond the role of a single mystery, turning them into tools for studying the inner life of globular clusters. Hubble data is well suited to this kind of research because it combines high resolution with observations through multiple filters. In the core, where the stars are most crowded, separating each source of light is essential. A small error in photometry can change a star's position on the diagram. A star whose light is blended with a neighbor may appear brighter than it truly is. With better resolution, Each member can be placed on the map more accurately, and the stars that are truly mismatched in age can be recognized with greater confidence. The more stars are measured correctly, the clearer the cluster's shared age line becomes, and the more meaningful the exceptions become. Hubble also shows the difference between seeing and understanding. To see a star cluster is to receive light from it. To understand a star cluster is to separate that light into many layers. Position, color, brightness, motion, spectrum, spatial distribution, and relationship. An image can make the viewer pause because of its beauty. A diagram can make an astronomer pause because one point lies in the wrong region. These two experiences are not opposed to each other. Beauty draws the eye toward the cluster, while data allows that ancient light to speak in a more precise language. In that process, blue stragglers do not naturally become the final answer. They are a doorway. Through that doorway, we enter the story of binary systems, mass transfer, mergers, cluster core dynamics, the survival of stellar pairs in crowded environments, and even the limits of reading stellar age from light. A blue point in the wrong place is both the result of a past history and a sign that allows us to trace that history backward. It is like a differently colored ink mark on an old map, small, easy to miss if we look too quickly. But once noticed, it makes the reader wonder what pen left it behind. There is also a kind of humility that needs to remain in how these signs are read. Not every unusual blue member can be firmly assigned to a single origin. In some cases, the data supports mass transfer. In others, merger seems more reasonable. In some, the cluster core environment plays a strong role. In others, more observations are needed to distinguish between possibilities. Science here is not a matter of placing one simple label on each star, but of weighing multiple possibilities against the best data available. That carefulness keeps the story from becoming either mystical or too simple. A star sitting in the wrong place on the diagram may have passed through a history we can no longer see directly. The stream of matter that once flowed between two stars has stopped. The companion may have faded. Two stars that once merged may have settled into a single object, with no old boundary remaining. The close encounter that altered an orbit may have happened billions of years ago. What remains is only the present light, the present motion, the present surface composition, and the present position within the cluster. From those remaining traces, astronomers reconstruct a past that no longer shines the way it did when it happened. That is why a Hubble image of a globular cluster can be both quiet and deep. In a single frame, everything may seem motionless. The stars lie like bright grains suspended in darkness. But beneath that still layer, the data points toward different histories. Some stars are aging along familiar paths. Some have left the main sequence. Some may have exchanged matter. Some may be the products of mergers. Some stand outside the line of age and show that the cluster is not only a place that preserves ancient stars, but also a place where stellar lives have interacted for long enough to create results that are not intuitive. When ultraviolet light makes the hotter members stand out, when filters turn color into data, when the color magnitude diagram reveals the order of the cluster, and when the displaced points are compared with their locations in the core or outer regions, a new story emerges from the dense crowd of stars. Hubble does not only photograph an ancient chandelier in space, it helps read each small light in that chandelier as its own sentence. Most of the sentences tell of shared old age. A few tell of detours, where a star received matter, where an orbit was altered, where two objects once blended into one. From this perspective, the blue members with the wrong apparent age are no longer disruptions in the picture. They are precious marginal notes in a very ancient manuscript. If we ignore them, the cluster is still beautiful, still old, and still useful for measuring age. If we read them carefully, the cluster becomes more alive. It is not only a collection of stars that formed and then aged together, but a system where age, mass, and environment continually influence one another. A few small blue points, are enough to remind us that even in a place that seems very old and very stable, history can still branch in many directions. At the end of the observing process, what is striking is not only that human beings have found unusual stars, but how they found them. Not with a quick glance, not with a feeling for color in a beautiful image, but by letting light pass through multiple filters, measuring each source, building diagrams, checking membership, tracking motion, reading spectra, and comparing many clusters with one another. A star that looks young among an old population only truly becomes a clue when it is placed within that entire network of data. The ancient chandelier of the galaxy, seen in this way, no longer merely shines. It is red. The stars do not only glitter, they are placed into an order of age. The blue points are not only beautiful, they become signs of interaction. Through the patience of observation, a globular cluster moves from spectacle to record, from record to history, and from history to a deeper story of how a star can carry, in its present light, part of the life of another star. Once the mechanisms have appeared and the observing method has become clearer, the picture still does not stop at individual stars. The story begins to widen toward the environment of the cluster itself, where binary systems are preserved, where they are broken apart, where mergers are encouraged, and where apparent rejuvenation is allowed to unfold slowly over time. The blue points with the wrong apparent age do not only answer that some stars have changed, they also place the globular cluster in the role of a natural laboratory, where gravity, stellar density, and immense time test many different paths for making the light of old age more complicated. A blue point lying outside the cluster's shared age first seems like the private story of one star. It is hotter, brighter, and more massive than expected in an old population. It may have received additional matter from a companion, or it may be the result of two stars that once came too close and blended into one. But the deeper we go into how these age-mismatched members appear, the more clearly we see that a star is never truly separate from the place where it lives. It has its own core, its own light, its own mass, but around it is a vast gravitational environment, where hundreds of thousands of stars move together, pull on one another very gently over long spans of time, and create opportunities that a solitary star in a sparse region of the galaxy would almost never encounter. From far away, a globular cluster looks like an ancient, round, quiet mass of light, as though every member inside it had been fixed in the same structure long ago. That feeling is only true on the outer surface of the image. Inside the cluster, space is not the same everywhere. The core is usually more crowded, the light is denser, and the stars pass closer to one another on astronomical scales. The outer regions are thinner, softer, less affected by gravitational encounters, and binary systems may be able to keep stable orbits for longer periods of time. Two stars may belong to the same ancient cluster, but if one star lives deep in the core and the other lies farther out in the outskirts, the gravitational histories around them can be very different. That difference makes the positions of the unusual blue members meaningful. A young-looking star in the dense core suggests a life surrounded by more close encounters, more moments when orbits were pulled off course, and more chances for binary systems to be tightened or distorted. A similar member in the outer region may suggest a quieter path, where a binary system survived long enough for one star to expand and transfer matter to the other. Position does not explain everything by itself, but it places the star in the right context. A blue point has not only color and brightness, it also has an address inside the cluster, and that address carries traces of the environment. Stellar density plays a subtler role than intuition first suggests. When a region contains more stars, close encounters have more chances to occur. A binary system may be altered by a passing star, causing the two inner members to move closer together. A pair of stars may be pushed into a state where mass transfer becomes easier. In rare cases, a chain of interactions may bring two stars toward merger. Seen in this way, A crowded region seems like a favorable place for producing blue points with mismatched ages. But crowding also has another side. Fragile binary systems need to survive long enough for mass transfer to happen. And if the environment is too chaotic, a close encounter may break the pair apart before it has time to create a younger-looking member. A cluster, therefore, does not work like a simple switch, where higher density always means more unusual blue stars. A region that is too sparse may lack the necessary influences to modify orbits. A region that is too crowded may destroy the binary systems that need to be preserved across billions of years. Between those two extremes is a slow balance. Stellar pairs must be durable enough to survive, but they may also need just enough influence for their life paths to turn in another direction. In that balance, the cluster becomes a natural filter, preserving some evolutionary paths and removing others before they can leave blue light on the diagram. Binary systems are important seeds for many age-mismatched members, but those seeds do not grow in the same way everywhere. A pair of stars in the outer region may orbit one another relatively peacefully for a very long time. The more massive member ages first, its outer layers expand, matter flows to the companion, and the receiving star becomes hotter and brighter. In the dense core, the same kind of binary may be pulled by a passing star, have its orbit tightened, or be broken apart completely. Some pairs are helped by the environment into deeper interaction. Others lose their chance before mass transfer can begin. The cluster does not only contain binary systems, it tests their durability over time. Close encounters do not need to create an immediate result. A star passing near a binary system may only change the orbit very slightly. That change does not make the star shift color in that instant, but it can place the binary on a new path. After millions or billions of years, the smaller distance may allow matter to begin flowing. A more elongated orbit may cause the two members to come very close during one part of each cycle. A system that was once stable may gradually enter a common envelope state and eventually merge. The cause may lie far in the past, while the result appears in the present as a small blue point on the color magnitude diagram. A globular cluster also changes its own internal structure. Through countless small gravitational interactions, more massive stars tend to lose some of their kinetic energy and gradually concentrate more toward the center, while lighter stars may be pushed farther outward. This process makes reading the positions of unusual blue members more complicated, but also richer in information. A star in the core may have been created there, inside the crowded region. It may also have formed somewhere else and then gradually sunk toward the center after becoming more massive. Its present position is not a simple photograph of its birthplace, but the result of an entire history of motion inside the cluster. This forces astronomers to look not only at individual stars, but at the population as a whole. A single unusual blue member may keep too many secrets in its past. Its companion may have faded, its orbit may have changed, the mass transfer event may have ended, or two stars that once existed separately may have merged into a single object. But when many such members are measured in the same cluster, and when many different clusters are compared with one another, patterns begin to appear. Where do they appear more often? Are they concentrated in the core or spread outward? Are they connected to the number of binary systems? Do they increase with stellar density, or do they decrease in environments that are too crowded? Each individual point may be quiet, but their overall distribution begins to speak in a slower language. In one cluster, the age-mismatched blue points may be strongly concentrated in the central region, where close encounters and mergers deserve attention. In another, they may more clearly suggest the role of long-lived binary systems in a less disturbed environment. Some clusters show a mixed picture, where both paths contribute. There is no rigid formula that applies to every globular cluster. Each cluster has its own density, its own age, its own dynamical history, its own number of binary systems, and its own traces of interaction. The unusual blue members, therefore, do not belong only to one type of star. They belong to the specific history of each stellar community. This way of seeing helps avoid an easy oversimplification. A place with more stars does not always produce more stars that look young. A quieter place does not always lack paths that can change apparent age. A dense region may create many encounters, but it may also destroy the stellar pairs that need to survive for a long time. A more sparse region may lack strong collisions, but it may protect binary systems long enough for mass transfer to occur. The same blue light on the diagram can come from different histories, depending on which paths the environment has helped or hindered. A globular cluster therefore becomes a natural laboratory that human beings could never build. No one can create a sphere of hundreds of thousands of stars, compress them into an ancient region of space, and then wait billions of years to see which binary systems survive, which ones are destroyed, which stars receive matter, and which stars merge. The universe has been doing that work for a very long time. Each cluster is a different version of the gravitational experiment. Some have denser cores. Some retain more binary systems. Some have undergone stronger core contraction. And in some, the age-mismatched members are distributed in ways that force us to reread the entire internal history of the cluster. In that laboratory, gravity works without noise. It does not need a dazzling spectacle to change an orbit. A star passes near a binary system, pulling gently, but enough to alter orbital energy. A pair of stars survives for a few more billion years. One member expands, and matter flows across a gravitational boundary. One star receives new mass, becomes hotter and bluer, and then appears in the wrong age position on the diagram. Each individual step may be almost invisible in a single image, but the long chain of them leaves a result clear enough for Hubble and other telescopes to measure. The environment inside a star cluster is not a passive background. It changes the probability of events, the lifetimes of binary systems, the chances that stellar pairs will reach mass exchange, the opportunity for mergers, and even the final position of a star after it becomes more massive. A star with the same initial mass, if it lives in a sparse region of the galaxy, may follow a fairly simple stellar life. If it belongs to a binary system in the core of a globular cluster, its orbit may be modified, its companion may be affected, and its evolutionary path may turn in an entirely different direction. A place in the universe is not only where light is emitted, it can be part of the reason that light has become what it is now. Looking back at the ancient chandelier of the Milky Way, each small light begins to carry more layers. Most stars tell the shared age of the cluster, following the main sequence turnoff and the familiar evolutionary branches. Some members preserve traces of binary systems. Some may be the result of matter transferred through the space between two stars. Some may have been remade through merger. Some lie in regions showing that the environment protected a stellar pair for long enough. Others are found in more crowded places where close encounters once altered their paths. The cluster is no longer only an ancient mass of light, but a network of gravitational relationships recorded in color and brightness. The distribution of the blue members with mismatched ages can also tell us how far the cluster has evolved dynamically. A cluster may be very old in stellar age, but its inner regions have not necessarily been rearranged at the same pace. The core usually experiences more interactions, while the outer regions keep a slower rhythm. If the blue points are concentrated in a particular pattern, or if they appear in different regions at different rates, that data can suggest how energy and mass have been redistributed over time. A small blue point then connects to the larger structure of the cluster, like a tiny mark on the surface of water that can reveal which way the current beneath is moving. These members with the wrong apparent age lie between two scales. On the scale of a single star, they are hotter, brighter objects that may have gained mass or once merged. On the scale of the cluster, they are products of density, binary systems, close encounters, orbital survival, and immense time. They are like small nodes in a larger network. From one blue point, the thread may lead to a faint companion. From that companion, it leads to an earlier orbit. From that earlier orbit, it leads to the core or the outer region of the cluster. From that region, it leads to the dynamical history of the entire stellar community. This understanding makes their youthful appearance feel less solitary. A star does not stand at the wrong age simply because it is strange by itself. It stands at the wrong age because it has lived inside some kind of relationship, in some kind of environment, through some chain of interactions. Its present blue light is the visible part of many things no longer directly present in the image. An orbit that was once closer, matter that once flowed from one star to another, a close encounter that changed a path, a binary system that survived long enough, or a merger that erased the boundary between two objects. When we look at such a blue point, we are not looking only at a star. We are looking at what remains of the forces that have passed through it. An ancient globular cluster becomes more real because of these exceptions. If every star followed only one simple path, the cluster would be easier to read, but also poorer. The blue points with mismatched ages do not deny the old age of the population. They give that old age more depth. They show that in a community that has lived for billions of years, not every member has preserved its original conditions unchanged. Some have been altered by a companion. Some have had their orbits edited by the environment. Some have merged with other stars. Most of the cluster remains a record of ancient age, but scattered through that record are small marginal notes about closeness, gravitational encounters, and shared matter. A Hubble image holds all of this in silence, but the data behind it makes that silence full of motion. The stars are not still. Binary systems are not entirely unchanging. The core is not only the brighter region, but the place where many orbits have passed closer to one another. The outer region is not only the sparser region, but maybe the place where some stellar pairs were preserved for long enough. Across billions of years, the cluster has aged as a population while continually modifying some of its members through small and rare interactions. The blue lights with the wrong apparent age are where those modifications become visible. After all these layers, the age of a star is no longer a simple number. There is the formation age, when the original matter gathered into a star. There is the apparent age, revealed through color and brightness. There is the orbital history, where the star may have lived close to a companion or been pulled by passing stars. There is the environmental history, where the cluster determines which binary systems survive, which are broken apart, and which paths are opened. A small blue point in an old cluster does not make time disappear. It shows that time in the universe can pass through many layers, from the stellar core to the orbit, from the orbit to the core of the cluster, from one individual member to the entire ancient stellar community. Within that chandelier, the lights with mismatched ages no longer seem like strange deviations standing outside the picture. They are part of what gives the picture depth. They show that an old star cluster can still contain detours of age, not because it is constantly forming many new stars like a young nebula, but because it has held stars for long enough for gravity, matter, and closeness to do their work. Some lights follow a straighter path. Others carry the traces of being pulled, replenished, and joined. All of them lie within the same star cluster, all shining in the same frame, but not every light has a history as simple as the others. An old globular cluster does not become young again simply because it contains a few blue points that sit outside the general order. Its ancient background is still there, written in thousands of stars that have traveled through a very long shared history. The main sequence turnoff still says that most of the population has aged. The lighter stars still burn slowly. The more massive stars from the first generation have still left their youthful positions long ago. The ancient chandelier of the galaxy is still an ancient chandelier. It is precisely against that background that a few blue lights with mismatched ages become meaningful, not because they erase old age, but because they make old age harder to read, deeper, and more real. At first, a star like this may feel like a small exception. It is hotter than expected. It is a little brighter. It lies in a place where a star in an old cluster should no longer stand if it had followed only the simple path of a single star. But once the layers of the story are opened, that exception no longer seems like something outside physics. It becomes a place where many processes meet. Its blue color speaks of temperature. Its brightness speaks of energy. Its position on the diagram speaks of evolutionary state. Its present mass speaks of a history that may have changed. The environment of the cluster speaks of orbits, binary systems, close encounters, and spans of time long enough for rare events to quietly accumulate into visible results. The youthfulness of these members is a youthfulness read from light. It is not like the youth of a newly born star in a young cloud of gas and dust, where matter has just gathered, the core has just ignited, and the surrounding population is still young as well. In a globular cluster, that youthful appearance has a different origin. It may come from matter received inside a binary system, from a companion star that aged first and left part of its outer layers to the other star. It may also come from a merger, when two old stars could no longer keep their separate boundaries and formed a more massive object. Along both paths, what appears is not a completely new beginning, but a turning in a stellar life that began very long ago. This changes the way we understand the word old in the life of a star. For a solitary star, age can seem almost like a straight current. Matter gathers, the core heats up, nuclear fusion begins, the star lives on the main sequence, and then leaves the stable stage when the fuel in its core changes. That path is still true for many stars, and it is exactly what allows astronomers to read the ages of star clusters. But in the real universe, not every star preserves its original mass. Not every star stays far from a companion, and not every binary system remains untouched by its environment. The age of a star can be written by the fuel in its core, then partly revised by matter from somewhere else. A blue straggler does not say that time has stopped. It says that time can leave marks in many ways. There is time inside the core, where hydrogen gradually becomes helium. There is time in orbit, where two stars revolve around one another through billions of silent cycles. There is environmental time, where a globular cluster holds its members inside a shared gravitational field long enough for rare encounters to become important. There is observational time, where light travels for tens of thousands of years to reach Hubble, is separated through filters, measured as data, and placed on a diagram so that human beings can recognize a blue point that does not sit in line. One small light can contain many kinds of time layered together. Seen in this way, the beauty of globular clusters also changes. They are not beautiful only because they are dense, ancient, and sparkling in the darkness of the galaxy. They are beautiful because they preserve so much history within a single view. One image may show thousands of stars at once, but each point of light has not necessarily passed through the same kind of stellar life. Most follow the shared order, regular enough for the cluster to be read like a clock. A few pass through detours, different enough to give that clock small, marginal notes. It is the coexistence of order and exception that makes the cluster feel more alive. Nothing in those blue points needs to be turned into a miracle. A star that receives additional matter still obeys gravity, pressure, temperature, and nuclear reactions like any other star. A star after a merger must still settle according to its own physics. Greater mass can make it hotter and brighter, but it can also make it consume fuel more quickly than lighter stars. Its youthful appearance does not guarantee a longer life. Sometimes, being made more massive also means that the fire inside burns more strongly. Blue light may be the sign of a new chapter, but that new chapter still belongs to the book of time. What is worth remembering is the difference between escaping age and being written by age along another path. These unusual blue stars do not escape growing old. They only make aging no longer look like a single road. One star may have been born with the cluster, lived quietly in a binary system for billions of years, received matter from its companion, and then appeared as a younger member. Another star may be the result of two older objects merging, carrying new mass and new light. Both still belong to the old cluster, Both still carry the traces of a long history, but their present light has been changed by their relationship with another star. That difference makes globular clusters no longer feel like static museums of the universe. They are ancient, but not dead. They are old, but not simple. Inside them, stars still move around the shared center. Binary systems still orbit one another. Orbits can still be gently adjusted. More massive members can still gradually concentrate toward the core, and stellar pairs can still survive or be broken apart. A globular cluster does not need to give birth to countless new stars in order to still have an inner history. It only needs to keep holding its members together, allowing gravity to work across spans of time that human beings can only measure through data and inference. In the quietness of a Hubble image, this can be very easy to miss. The image does not show the orbits changing. It does not show matter that once flowed from one star to another. It does not show a binary system tightening, a common envelope surrounding two stellar cores, or a merger settling into a stable point of light. The image only shows the light that has reached the detector. The rest has to be read through color, brightness, position, motion, spectrum, and the distribution of stars within the cluster. Astronomy here is like a very long kind of listening, where events that have passed no longer make a sound, but still leave rhythm in the data. One of the gentlest things about this story is the way it brings closeness into the universe. Stars are often imagined as objects so far apart that they are lonely, each one a separate sun, each point of light, a closed world of its own brightness. But these members with mismatched ages remind us that closeness, in the gravitational sense, can change an entire stellar life. A companion star does not need any intention to help or to destroy. It only needs to be close enough for long enough. Matter will follow attraction. Orbits will respond to the loss and gain of mass. Stellar cores will change, according to the new structure, and the outer light, in the end, will tell us that this star once did not live alone. There is a kind of peace in the way the universe preserves connections like these. Not through memory, not through words, not through a direct image of the event, but through the present state of matter. A faint white dwarf beside a star may be the trace of the one that gave material away. A high rotation speed may suggest accretion or merger. A displaced position on the diagram may show that mass has changed. A concentration in the core may speak of a crowded environment. All of these are physical ways of preserving the past. What happened may no longer be visible as a scene, but it still lives in its consequences. When we return to the image of NGC 6723, the chandelier cluster is no longer only a beautiful collection of points of light. It becomes an ancient room of the galaxy, where each light has been placed into its own time. Most of the light within it lets us feel the endurance of small stars, the long life of a globular cluster, and the patience of gravity, holding a stellar community together for more than 10 billion years. A few bluer lights suggest something else, not a betrayal of old age, but evidence that, within the same ancient place, some members have passed through deeper relationships with neighboring stars. The cluster is still old. The blue points only give that age a few bright cracks, where its inner history begins to show. The way human beings recognize this also has its own beauty. No one looks up at the sky with the naked eye and immediately sees a star standing in the wrong position on an evolutionary diagram. No one can look only at the color blue and know its history for certain. Human beings have to place telescopes beyond the atmosphere, gather light that has traveled 27,000 years or more, separate that light through filters, measure individual stars in a crowded region, reconstruct the order of the cluster, and then search for the points that deviate from that order. The youthfulness of a star only becomes science when it is placed beside the ages of thousands of other stars. That makes understanding humble. We do not see the entire past. We do not have a film showing one star receiving matter from its companion for millions of years. We do not have clear footage of every merger that created blue points inside an ancient cluster. We have present light, physical models, spectral signs, position within the cluster, tiny motions over time, and comparisons among many star clusters. From those remaining pieces, science builds the most reasonable paths. The incompleteness of the data does not make the story less valuable. It makes the story feel more real, because the universe rarely offers its past as one complete answer. The stars that look young inside old clusters are therefore not a mystery meant to make the listener tense. They are a gentle reminder that nature is often more complicated than the first straight lines we draw. A star is not only its initial mass. It may or may not have a companion. It may live in the core of a cluster or in the outer region. It may or may not be pulled by passing stars. It may or may not receive additional matter. It may or may not have merged. These things do not destroy the order. They add depth to it. The cluster still has an age. The main sequence still has a turn-off point. Stellar evolution still has its laws. But within those laws, there is room for private histories. Within the vastness of the universe, this thought can feel very soft. A star does not need to be the center of a galaxy to carry a complicated story. A tiny blue point, almost lost among thousands of other lights, can still contain the trace of two stars that once orbited one another, of matter that once left an expanding envelope, of an orbit that once tightened, of a cluster environment that held everything long enough for a rare event to happen. Smallness in an image does not mean simplicity in history. Some things are small only because they are far away, not because they carry little meaning. If the listener places themselves before an image of a globular cluster, there is no need to immediately find each unusual blue member by eye. It is enough to notice the feeling that, within that ancient glow, not every point of light is telling the same kind of time. There are stars burning slowly along their own paths. There are stars that have left the main sequence. There are fainter remnants of stars that have aged. And there are a few blue lights that look as though they arrived late, not because they were just born in a new generation, but because matter and gravity have given them a different position on the map of age. From there, the globular cluster becomes a new way of seeing time. Time is not only something that makes everything grow old at the same rhythm. It is also a space long enough for relationships to reveal their consequences. In one day, two distant stars may change almost nothing. In 1,000,000 years, an orbit may shift. In 1,000,000,000 years, a binary system may move from stability to mass exchange. Across 10 billion years, a star cluster can preserve both the general rules and the exceptions created by interaction. Time does not only make stars grow old, it also allows stars to change one another. The blue lights in an old star cluster do not refuse time in the sense of resisting it. They have passed through time, been shaped by time, and can only appear because time has been long enough. If the cluster were young, their blue color would not be surprising. If a binary system had not lasted long enough, matter would not have had time to transfer. If the cluster were not ancient enough, the age mismatch would not be clear. Time itself creates the background against which the unusual appears. They are not proof that time has failed, but proof that time can work along many detours. In the end, what remains is not the feeling that a few stars have tricked the universe. What remains is another kind of stillness. Even the age of a star has history, environment, and relationship. A star can age in its core, while its light is changed by matter from a companion. A cluster can be ancient, while quiet interactions continue inside it. An image can be motionless, while the data within it still preserves the traces of very long motion. A blue point can look young, but that youthfulness does not erase the past. It carries the past in another way. The ancient chandelier still hangs in the darkness of the Milky Way, so far from Earth that its light must travel tens of thousands of years before reaching us. In that cluster, most of the light tells of the slow aging of ancient stars. A few other lights tell us that some stellar lives did not travel alone. They once shared matter, once felt the pull of orbit, once were guided by the cluster environment into different paths. They shine blue against the old background, not as escapees from time, but as small signs that time in the universe is not one single straight line. As that light continues through space, it does not hurry to explain itself. It simply arrives, one photon at a time, carrying color, brightness, and the trace of a very distant history. Human beings receive it, measure it, place it on a map, and realize that an old star cluster can contain a few stars that look young without losing its ancient nature. Perhaps that is the gentlest part of the story. The universe does not need to be simple in order to be peaceful. Sometimes, peace comes from understanding that even exceptions have their place, and that even lights with the wrong apparent age are only telling another path through the same vast time. Perhaps what makes these blue lights with mismatched ages memorable is not that they are overwhelmingly bright. In a globular cluster, they are only a few small points within a sea of ancient stars, and without diagrams, without color data, without ultraviolet light, without patient measurements, they could easily dissolve into the cluster's shared sparkle. But that smallness is exactly what makes the story gentler. The universe does not always hide profound things inside its largest spectacles. Sometimes, one point of light displaced from its expected position is enough to open an entirely different way of seeing stars, age, closeness, and what can happen when gravity is given billions of years to work. An old globular cluster is like a reminder that the universe has its own kind of memory. It does not remember in language. It does not preserve the past in clear images the way human beings keep an old photograph. But it leaves consequences in matter. An orbit that was once pulled off course may still be preserved in present motion. A star that once received matter may still preserve that event in its present mass and color. A merger that settled long ago may still be preserved in rotation speed, in position on a diagram, in a blue brightness that does not match the shared age of the cluster. What has passed does not disappear completely. It changes form, from event into structure, from motion into trace, from the past into present light. When we look at an ordinary star, we often think of it as a hot sphere of gas burning through nuclear fusion. That way of thinking is correct, but it is not enough to touch the full depth of an ancient star cluster. A star is not only its core, it is also its orbit, the environment it lives in, the objects that have passed close to it, and the companion that may once have shared with it a common center of gravity. Stellar life does not only unfold from the inside outward, from core to surface. It also unfolds from the outside inward, when matter arrives from another star, when an orbit tightens, when the cluster environment allows a stellar pair to survive or fall apart. A blue point in an old cluster is therefore not only a hotter star. It is a place where the inside and outside of stellar life meet. This makes the story of Blue Stragglers very different from simple ideas of youth and old age. In everyday life, young and old are often placed at opposite ends of a straight line. Something is new, then old. A day begins, then ends. A flame is lit, then fades. But in stars, especially inside crowded and ancient clusters, that straight line can bend. A star may form very early age along with the cluster and later receive additional matter. A binary system may hold two members together across a long stretch of time, so that when one star expands, its outer layers become part of the other star. Two stars may merge, not creating youth out of nothing, but joining two old histories into a brighter, hotter, more massive structure. When that happens, the light does not lie, but the light also does not tell everything in one simple sentence. The blue color is real, the high temperature is real, the greater brightness is real, the displaced position on the color magnitude map is real. What requires caution is the way we read that truth. If we rush to see it as the sign of a newly born star, we forget the ancient environment of the cluster. If we rush to call it a star beyond time, we forget the physics that changed it. The gentler and more accurate reading is to see it as a star whose apparent age has been rewritten by a history that was not solitary. In the middle of a globular cluster, Such a blue point is like a sentence in an old book written in a slightly different ink. The book is still old. Most of the pages still carry the color of time. The main text still shows that it has existed for a very long while. But that different ink makes the reader pause. It does not ruin the book. It makes the reader realize that the book was once touched, once revised, once passed through another hand before reaching the present. With stars, there is no hand at all. There is only matter, gravity, and orbit. But the feeling of one history layered over an older history is still there. Globular clusters also show us a kind of community very different from human life. Stars do not know that they are inside a cluster. They have no awareness of the members beside them. They do not choose to pass close to one another. Do not try to help one another. Do not hold one another in place out of affection. But gravity still creates relationships. It makes two stars orbit one another. It pulls a stream of gas from one star to another when the conditions are right. It tightens orbits through close encounters. It holds the whole cluster in a great sphere for billions of years. The relationships here have no emotion, but they have consequences. And sometimes those consequences are large enough to make a star stand in the wrong position on the age clock of the entire cluster. The longer we look at clusters like these, the harder it becomes to use the idea of loneliness in the universe. The distances between stars are still enormous. The space between them is still so wide that imagination can easily become tired. But vastness does not mean absence of relationship. A binary system can be bound across a very large distance. A star cluster can hold hundreds of thousands of members inside the same gravitational field. A passing star may not touch another star, but it can still pull its orbit slightly off course. Given enough time, those small changes are no longer small. They become new life paths, possibilities for mass transfer, a merger, a blue light appearing in an image. This is why time in globular clusters feels so different from time in ordinary life. For human beings, a century is already long. For an ancient star cluster, a century is almost not enough for a small change to become clear in stellar orbits. 1,000,000 years may still be only a short rhythm in the life of a binary system. 1,000,000,000 years begins to allow slow processes to reveal themselves more fully. Globular clusters live in a kind of time where rare events do not need to hurry, they can wait. Gravity can repeat its influence through countless orbits, until a binary system reaches a moment of mass transfer, or two old stars are brought into one new form. A Hubble image compresses all that duration into a single visual moment. The viewer sees only one frame. The light appears still. The stars do not shift position before the eye. No stream of gas is visibly flowing through the image. No two stars are seen merging second by second. But behind the frame is very deep time. Each point of light has sent photons across space for tens of thousands of years. Each position on the diagram is the result of billions of years of evolution. Each exception is the trace of one or more events that happened so long ago that the present now preserves only their consequences. The image is still, but the causes beneath it have moved across immense spans of time. Blue stragglers also make the precision of science more beautiful. If we used only vague language, we might say they have become young again, have been revived, or refused to grow old. Those phrases are evocative, but beneath them there needs to be care. They look younger because their present light resembles the light of stars that are hotter, more massive, and less evolved than expected for the shared age of the cluster. They may have received additional matter or merged. They have not reversed their entire past. They have not escaped nuclear fusion, pressure, gravity, or the gradual exhaustion of fuel. The beauty lies in the fact that science does not need to turn them into miracles. Their physical truth is already strange enough and gentle enough. A star that has received additional matter is not renewed like an object wiped clean. Inside it there is structure, layers of material, and a core that has already passed through part of its own life. New matter can change its mass, alter pressure and temperature, and move it to a bluer position on the diagram, but it does not erase every internal trace. A star after a merger is the same. It is not a blank sheet of paper. It is the result of two old pages joined together, where some lines have been mixed, some traces have been covered, and some new properties have appeared. The present light is simpler than the history that created it. This makes the blue points in an old cluster a lesson in not reading appearances too quickly. The appearance of a star is real data, but real data still needs context. A blue star in a young nebula may be a newly born star. A blue star in an ancient globular cluster may be a member that has been fed with additional matter. The same color, in two different environments, tells two different stories. The universe is not understood only by measuring each object separately, but also by placing that object where it belongs. Context does not change the light, but it makes the meaning of the light deeper. If we look back at the entire star cluster, those blue lights are like small openings through which we can see into a larger history. Most of the stars in the cluster create the shared background, like the long, even resonance of an ancient chord. The age-mismatched members add a few different tones, not breaking the music, only giving it more depth. They tell us that some stars did not keep a solitary path unchanged. Some orbits touched one another through gravity. Some material changed owners. Some binary systems survived long enough for one member to age first and give its outer layers to the other. Some mergers left behind a new star that is not entirely new. Their existence also helps us understand why globular clusters are so valuable in astronomy. They are not only beautiful objects to photograph, they are stellar populations that can be read as natural experiments in age. Because many stars in a cluster formed at nearly the same time, the differences between them become easier to recognize. Because the cluster is old, the original massive stars have had time to leave the main sequence. Because the cluster is crowded, interactions between stars have had opportunities to leave traces. Because the cluster has been held together by gravity for a very long time, rare events can accumulate into a small but meaningful population. A globular cluster is a place where both order and exception help science understand more clearly. In that setting, Hubble and other telescopes are like ways of gently drawing back the curtain from layers of light. First comes the separation of individual stars from the shared glow. Then the measurement of color through multiple filters, then the building of a diagram that reveals the cluster's line of age. Next comes the search for points standing higher and bluer than where they should stand. After that comes the check of whether they truly belong to the cluster or only lie along the same line of sight. Then come motion, spectra, position in the core or outer regions, the possibility of a companion, signs of rapid rotation, or unusual chemical composition. Each step does not make the star more mysterious. Each step makes the mystery more specific, more measurable, and more grounded in physics. There is also patience in accepting that not every history can be fully reconstructed. One blue point may have come from mass transfer. Another may come from merger. Another may carry traces of several processes layered together. At great distance, in a crowded field of stars, after billions of years of change, the past no longer leaves behind every piece of evidence. Science does not need to fill that gap with exaggeration. It can keep the gap in its proper place, as an unknown region surrounded by known facts. That feeling suits the universe more closely, clear in some layers, open in others, firm enough to understand, wide enough to keep curiosity alive. The stars with the wrong apparent age also bring human beings back to a gentler thought about observation itself. We often look at the sky and see a present moment. A star is shining, a cluster is there, an image is visible on a screen. But in astronomy, the present is always made from many pasts. Light takes thousands or tens of thousands of years to reach us. The state of a star has been shaped by billions of years of evolution. The blue color of an age-mismatched member may be the result of an event that ended very long ago. When we look at a globular cluster, we are never looking at a simple moment alone. We are looking at many layers of time placed on top of one another within the same field of stars. That can make the sky feel farther away, but it can also make it feel more peaceful. Farther away, because each point of light opens into a depth that the naked eye cannot grasp. More peaceful, because nothing needs to be understood all at once in a single glance. The light has patiently traveled through space. The cluster has patiently held its members together. Binary systems have patiently orbited one another. Astronomers, too, must patiently measure, compare, check, and place each point of light into the larger picture. There is a gentle correspondence between the way the universe unfolds and the way human beings learn to understand it. Slowly, layer by layer, without rushing everything into an answer that is too short. Within that slowness, Blue Stragglers no longer seem like rebels. They are more like small storytellers in an ancient crowd. They say that some stars have been changed by companions. Some stars have received matter and carried a different light. Some stars are the result of two histories joining together. Some regions of the cluster preserved binary systems long enough, or brought them closer together. Some gravitational encounters happened without anyone seeing them, but their traces remain in the present color. They do not deny order. They show that the order of the universe can contain detours. Perhaps that is what makes this story suited to a quiet night. It does not need to lead the listener toward fear. It does not need to make destruction the central focus. It does not need to turn stars into mystical objects beyond physics. It simply places before us an old star cluster, then points to a few blue lights within it, and from those small lights opens a softer truth. In the universe, growing old does not always happen alone. A star can carry part of another star's life. A cluster can preserve the traces of many encounters. A present light can be the result of relationships that passed long ago. When all of this is placed back into the image of the ancient chandelier, the picture does not lose its first beauty. It becomes more beautiful. The points of light are not only points of light. They are stellar lives. The colors are not only colors. They are temperature, mass, apparent age, and traces of interaction. The core is not only the brighter place. It is the place where many orbits have passed closer to one another. The outer region is not only the sparser place. It may be where some binary systems were preserved for longer. A few blue lights do not only add contrast to the image. They give the entire cluster a deeper sense of time. The peace at the end of the story does not come from everything being completely explained. It comes from the main pieces finding their places. Blue stars in old clusters were not necessarily born late. They may have been made to look younger through matter or merger. Binary systems allow stellar lives to touch. The cluster environment determines how likely those paths are to happen. Hubble helps human beings read that age mismatch through light, diagrams, motion, and position. The things still unknown do not break the picture apart. They simply leave a soft darkness around what is understood, like the sky still surrounding a glittering star cluster. A small blue point in an ancient cluster therefore becomes a very gentle reminder of the limits and possibilities of seeing. The human eye may only see the shared beauty. A telescope separates that beauty into individual sources of light. Data turns each source into a position on the map of age. Theory connects that position with mass, fuel, binary systems, and environment. From one point of light, human beings can trace a path through many layers of physics. Not to remove the beauty of the sky, but to see that this beauty has structure, history, and very real turnings within it. The ancient chandelier still lies in the darkness of the galaxy, unaware of what name it has been given, unaware that its light has reached Earth, unaware that human beings are reading the age of each member within it. The stars continue to evolve. Some binary systems continue to orbit one another. A few members may continue to change in the very distant future. The blue points we see now will also leave this state someday, because no light is exempt from time, But in the moment when their light reaches us, they show something deep enough to remain. Time does not only take away. Through gravity and matter, time can also connect stellar lives to one another, allowing an old star to shine as though it has been given a new path. And if an old star can shine as though it has just been given a new path, then its blue appearance is no longer something separate from time. It becomes one of the ways time leaves its own mark in matter. In the sky, that point of light is still so small that, standing alone, it almost says nothing to the human eye. But when it is placed back among the old cluster, among members that have traveled together for billions of years, it begins to carry another meaning. It does not make the cluster young again. It does not erase the layers of age already held in the yellow, red, and faint white light of ancient stars. It only shows that even in a very old community, a few stellar lives can still change direction because they once came close enough to another life. The gentlest part is that this change in direction does not need to break the order. A globular cluster still has a main sequence turnoff. The stars still obey the relationship between mass, temperature, brightness, and the rate at which fuel is consumed. More massive stars still burn faster. Lighter stars can still endure longer. Hubble can still read the age of the cluster by measuring thousands of points of light and placing them on a color magnitude map. The unusual blue members do not make those laws collapse. They simply stand in places where the laws need to be expanded to include binary systems, mass transfer, mergers, and the crowded environment of a globular cluster. That is a very different kind of understanding from finding an exception and throwing away the entire old framework. In science, an exception is most valuable not when it destroys everything, but when it points to a missing layer. If most of the stars in a cluster follow a predictable order, then the displaced points become meaningful. If every star were scattered randomly across the diagram, one blue point would only be another point. But when the ancient stellar population arranges itself into clear branches, when the turn-off point reveals the shared age, and when regions on the diagram can be read as traces of evolution, a few blue members above the turn-off become quiet reminders that stellar life does not exist only in an isolated version. The simplest story of a star can be told from its initial mass. It forms from gas and dust, reaches equilibrium, burns hydrogen in its core, and then evolves as the fuel changes. But a star in a binary system needs additional sentences. It has a companion. It has a shared orbit. It can receive matter or lose matter. It can be drawn closer over time. It can merge with another star and become an object that no longer resembles either original member. When all of this is placed inside a globular cluster, stellar life gains another layer of environment. Stellar density, the core, the outer regions, close encounters, the survival of binary systems, and a dynamical history extending across spans of time that are almost impossible to feel directly. Blue stragglers lie precisely at the intersection of these layers. They are stars, but they are also traces of binary systems. They are points of light, but they are also results of orbits. They are blue, but that blue does not only speak of present temperature. It also suggests a changed mass, matter that once moved through the space between two stars, or a merger that may have settled down long ago. In the simple appearance of a point of light, many things have been compressed. An image preserves only the light. Data and physics open that light into history. When we return to NGC 6723, the ancient chandelier is no longer only a beautiful object hanging in the darkness of the galaxy. It becomes a place where time is read in many voices. There is the voice of the whole cluster, ancient and slow, appearing through the overall shape of the diagram. There is the voice of the small stars, still enduring on the main sequence, continuing to burn at an economical rhythm. There is the voice of stars that have left the stable stage, expanded, and moved into later branches. And then there are a few thinner voices, bluer and more displaced, telling us that some members have not passed through age along their original straight path. Those thin voices do not need to be louder in order to matter. In a very slow piece of music, sometimes one slightly different note is enough to make the listener recognize the structure underneath. The unusual blue members do not make up most of the cluster. They do not overwhelm the population. They certainly do not turn the globular cluster into a young star-forming region, precisely because they are few, because they are displaced, because they appear against an old stellar background. They keep their power to suggest. An exception that becomes too common turns into a new rule. An exception that is rare enough makes the old rule clearer, while also showing that at the edge of that rule, there are side paths. One of those paths begins with the sharing of matter. Two stars orbit one another for a long time, perhaps very peacefully at first, until one member ages first and its outer layers expand far enough. Hot gas is no longer held completely by the donor star, and it flows across a gravitational boundary toward the receiving star. The star that receives matter gains mass, changes structure, becomes hotter and brighter. When observed from very far away, that entire long process contracts into one blue point. The viewer does not see how the stream of matter once flowed. The diagram only shows the result, a star that looks younger than the place where it belongs. Another path passes through merger. Two old stars, through interaction in a binary system, or through close encounters in a crowded environment, may reach a point where they can no longer remain independent. Matter mixes, the old orbit is lost, and a new, more massive object appears. It is not new in the sense of having just formed from primordial gas and dust, but it is new in the sense that its physical structure has been rearranged. Its light may be bluer, brighter, and positioned above the cluster's turn-off point. Once again, what is visible in the present is only the calm surface of a history that was once far more complicated. Between those two paths lies the environment of the cluster. If the cluster is too sparse, close encounters become less important. If the core is too crowded, many binary systems may be broken apart before mass transfer has time to happen. If the conditions are more balanced, some stellar pairs may survive long enough while also receiving just enough influence for their orbits to shift toward exchange or merger. A globular cluster is like a place where gravity continually filters possibilities. It has no purpose, but its conditions decide which paths can survive long enough to become light. Through this, the age of a star becomes more like a record with many layers than a single number. There is the age from formation. There is the apparent age read from color and brightness. There is the history of mass, because the star may not have kept the same amount of matter it was born with. There is the orbital history, because it may once have revolved around a companion or been pulled by passing stars. There is the environmental history, because the region where it lives inside the cluster may protect or break apart those relationships. When a blue member with the wrong apparent age appears on the diagram, it brings all these layers together into one point. This makes the stillness of the cluster deeper, not weaker. Knowing that inside a static image there are orbits, interactions, and detours does not make the image noisy. It only gives that stillness depth. Just as an old room can be quiet while still carrying the traces of many generations that have passed through it, a globular cluster can be silent in an image while still containing events accumulated across billions of years. The stillness is not there because nothing has happened. The stillness comes from everything unfolding at a rhythm too long, too vast, and too slow for a human lifetime. In this story, Hubble is like an instrument that helps make that slowness readable. It does not make the cluster older or younger. It does not create the blue points. It only gathers light sharply enough to separate members in a crowded region, sensitively enough to measure color through many filters, and patiently enough across observations to turn a faint glowing mass into a map of individual stars. When the light is placed on a diagram, the quietness of the image becomes a structure that can be understood. The blue point is no longer only a color. It becomes a position, data, a physical question, and then a clue to a history of interaction. There is a special beauty in the fact that science does not stop at the beautiful image. A photograph of a globular cluster is already enough to make a person feel small before the universe. But when the image is measured, when the light is analyzed, when each star is placed into order, the beauty is not reduced. It becomes more precise. We do not lose the chandelier when we learn that each point of light is a star. We do not lose the sparkle when we learn that blue is a trace of temperature and mass. We do not lose the strangeness when we learn that a young-looking star may have received matter from a companion. On the contrary, understanding gives beauty another depth, like seeing the delicate structure inside a form that was already beautiful. The blue lights with mismatched ages also remind us that not every strange thing needs to be told through tension. They do not threaten Earth. They do not warn of a catastrophe. They do not need to be turned into a dark mystery to hold attention. Their attraction comes from a slight displacement, from the way a small detail makes us reread the entire context. A hotter star in an older place, a younger light against an ancient background, a position that does not fit, and from there, an opening into binary systems, mass transfer, mergers, and the dynamics of star clusters. Sometimes the universe does not need to shout. It only needs to place one small point in the wrong place.